Well, good morning, everyone, and I guess good afternoon if you're in Middle East or in Europe. Welcome to this first knowledge sharing session of the year related to the Multiphase RTA Consortium. We have three of these this year. This is the first of those three. We'll get back to a little bit details on the other ones later. But the two first ones are essentially virtual. So like these, and they're 3 hours. Try to get 9 presenters in for each knowledge sharing session. And then the last one is a full day in-person event, but you can also join hybrid. That's here in Houston. My name is Matthias Carlson. I have several of my colleagues here with me today. I'm going to just kind of kick this meeting off and also facilitate the different presentations. And the format is very simple. Everybody will present for between 10 to 15 minutes, and then there's a Q&A session just after that. Just note that we are presenting and that we are also recording. Yeah, it's early in the morning, even for me. So we're recording, and the recording will be distributed after to all the participants. So if you have to, I've seen already, I've gotten a lot of text and emails that some people will have to leave, and some people can't attend the first part, etc. But just be aware that this recording will be available for forever. We have a lot of goodies on the presentation list today. As I mentioned, these first two sessions, they're a little bit shorter and what I call short and sweet compared to the last one. And today we're going to try to cover topics related to bottomhole pressure automation. I'm going to bring this into kind of a nodal analysis production engineering space before we wrap up with both some RTA, flow material balance, reservoir engineering related topics before Tedja's going to round it off with something on kind of well testing and DFITs. So just to go through this one-on-one, this is kind of the update presentation from me. I'll go through a few updates of what's in Wits and Plus that's new, but also primarily what's to come in the next few months in terms of our technical roadmap, and also give just a brief update on the JIP itself. Some of the presentations that you'll see today, for instance, from Leslie, is kind of a direct outcome of the joint industry project. So we're looking forward to that. The second presentation is Wade from Camino. He's going to go through a few things related to bottomhole pressure optimization and how that's done and implemented internally. Mark is going to do something similar on how they do that at the Diamondback, but also focusing on something he has been kind of an advocate for the last few, I guess, quarters and months. Is basically what we call BHP calculation settings. So what to actually do in the edge cases where you don't have good data. If you have a rod pump calculation without liquid levels, if you're on gas lift but you don't have gas lift rates for whatever reason, if you're on ESP and you don't have any gauge pressures, for instance. Then Graham is going to go in and talk a little bit about our newest feature in Wits and Plus, which is a starting point for nodal analysis that we've developed with Devon and also other companies. And he's going to show how you can use it to do some simple design and optimization of gas lift and Wits and Plus. Then John is going to go in and give us a little bit of the history of how that feature was implemented. And that's been a very popular feature already, and we see that there's tons of room for improvement as well, which is great. And there's going to come a lot of updates on that feature in the near future. But it's going to be a great starting point to look at a few case studies and also to look at where it comes from. Then we're going to switch gears a little bit, talk a little bit of broadly, probably dipping our toes more into what we can do on the subsurface point of view. So Mo is going to go through very quickly 10 different things you can do in Wits and Plus in 10 minutes. So basically 10 case studies in 10 minutes. That's going to be pretty cool. Before our friend from Crescent Point will go through a very, very impressive RTA study in the Bakken. Very large data set, a lot of different types of analysis. So really excited about that from Gaurav. And Leslie, he will go through the multiphase flow material balance method, but now applied for well groups. So let's say you want to do it for a bunch of wells on the same pad. what do you actually do then in practice. Maybe you have a pad where different wells are coming on. We might have a parent well and you might have a children well. They might be communicating, et cetera, et cetera. So he's going to actually show both simulated cases of that, where he tests basically what he's come up with and I guess some of the theory there as well, before we look at actually a case study in the Permian. The last presentation is kind of I would say maybe a teaser for what's to come later this summer. That's Teja, or we call him Teja, I guess. A lot of you know him as Venkata. He is spearheading kind of a DFIT initiative to be able to interpret DFIT. So he's going to give you a very brief overview of what you can do with a DFIT, why we do a DFIT in the first place, and how it's done. In terms of the timeline of the consortium, it's kind of a 4-quarter consortium. The first part of the first quarter was end of last year. That was basically to get everybody up to speed into the software, making sure the wells were connected to their databases, etc. The second quarter is where we are right now, and we're basically wrapping up the second quarter today, actually, with this knowledge sharing session presentation, and in the next few quarters we have dedicated knowledge sharing presentations as well. The whole consortium is being wrapped up in what we call WITCon. We thought that was a great word for basically a full day event, an excuse to have a full day event only with well performance topics. That's an in-person event here in Houston. Last year we had around 50 in-person participants and about 50 people also joining online, and it was great to see a full day of both presentations and also people analyzing, for instance, the same well but just different interpreters. That was really successful as well. So we're going to do more of that, and we also had a panel session including some social activities. So that was a very good way for us to meet in person. Also kind of get some cross-pollination across the companies, and I know for sure that that meeting and also being a part of the consortium has facilitated a lot of these talks across companies that, for instance, work in similar basins and similar areas to brainstorm on what they're seeing, etc. As you all know, we have 5 different small courses throughout the year. All of them are virtual. They're complimentary, so if you want to join them, send me an email and I'll send the invite out. And they try to be hands-on with both the software and theory. So we try to cover the theory and show you how you can apply that in practice. The first one is already done. The recordings are here for the different sessions. For those who remember, it was a little bit of a drama because it was actually our office here in Houston at the consulate in Houston. It was actually a bomb threat at the consulate that day. So we had to take a little bit unexpected break there, but hopefully the last courses right here will not have that degree of drama associated with them. So the next course there is 27th of April, and then there's one in June, one in August, and one in September on dedicated topics. So these courses are a little bit different than the ones that we do for a lot of you in person. So the ones in person is kind of like a half day, get through everything in a half day, a little bit rushed, while these are dedicated to specific items. PVT only focusing on PVT theory and associated functionality in the software for half a day. And then we're doing similar things on bottomhole pressures, similar things on RTA, flow material balance, etc. So again, if you have not received an invite to these courses and you want to attend, send me an email and I'll make sure to get you on that list. For the the audience here today is a big mix of some people just started to work with us, some have worked with us for probably 3 years now, and everything in between. So just to make sure everybody's on the same page when it comes to kind of our vision and what we like to try to do with at least when it comes to Wits and Plus, and also to make sure that everybody has a little bit of basic background, at least on some of the RTA items before we get started. I thought to just run through that really quick and then give the word to Wade here, and hopefully 5 minutes. So Wits and Plus was a software we decided to start developing a little bit more than 2 years ago now. So that was when the first line of code was written. And then since then, we've been really lucky to get very good adoption in the industry. And I think these consortiums have really helped with that adoption. And now we see there's several hundred people logging on and using the tool every single day. And what we've tried to do from the get-go is to make the solution very simple. That means in every part of the word, making it one product, including all the features that we are developing right now and all the future ones that we are releasing. So for instance, when I mentioned DFIT, that is going to be released hopefully sometime this summer, that is not something you have to pay extra for. That's a part of the product. The same goes for the other features that I'll show in the roadmap in a minute. It's also one price for unlimited number of users, so there's no, there's no one blocking your licenses internally in the company when you need to use it. We try to keep it in one interface such that you can do everything in one interface and log on to that in a very simple manner. Just going to your company domain.wits.com and logging in with single sign-on. And we've had a push to get a lot of you on single sign-on now. And from now on, we're probably going to require all of you to do it. And the reason for single sign-on is so important is if you have a resource, for instance, that is getting onboarded, it's very easy for us then to, of course, go to the web page. They don't have to include us. They can just log in with their office credentials. But more importantly, if that resource for some reason is leaving the company or is not with the company anymore, that email address is deactivated, so they're not able to log into the tool anymore. If you had to have a manual account then, and you'll have usernames and whatnot floating around, they will actually still have access to the tools. It's a huge security risk if you're not transitioning to single sign-on. So if you're still not on single sign-on, you need to ensure that you've reached out to Jason or me to make sure that your company is on single sign-on. The last thing that I will mention is that our goal, like we can talk about the vision of the product, etc., but like our most important goal in the company when it comes to WITS and POS is to make sure we have the best support there is. So if you send a message to us and there's not someone getting back to you in less than 10 minutes or in 2 minutes, I'll be very surprised. And we're always trying to making sure that people are getting their questions answered very fast and getting their problems helped with. And if there's bugs, we try to fix them ASAP. And if there's feature requests, we will always let you know if that's in the development roadmap, if we add it into the implementation backlog, and how high on the priority list it is. The last thing for you is, like, I know probably 70–80% of the companies here, they have already done a so-called cloud integration, which just means that they're using the API or external API to basically flow internal daily data into the solution, or they're using a Snowflake share connection. The end result of both of these is essentially that you get daily production data in your software. And you can also automatically calculate, for instance, bottomhole pressures or separator shrinkage factors on a daily basis. The reason why I mention this is that if you are in one of the few companies that has not set this up yet, make sure to reach out to us so that we can get this up for you ASAP. And this is not a big lift, actually. We can set that up for you in one day. And we have several case studies of companies with hundreds of wells that have everything flowing through the system, in 3–4 days. So just let us know if you haven't done this yet, and we'll be happy to help. Last thing before I'm jumping into some of the RTA pieces is kind of the most popular workflow that's hopefully going to set the stage for some of the presentations early today. Is the technology related to combining production data, wellbore on artificial lift data, a cloud integration of choice to calculate bottomhole pressures on a daily basis. So you can integrate, for instance, your well view database or something equivalent to that and your production data to calculate bottomhole pressures, such that every time you go in and want to do analysis that you're working on greenfield wells, so wells that has fresh, new production data flowing through it. That said, we're going to talk a little bit about, there's going to be probably 3–4 presentations in the RTA realm today. So I thought just to give very, very brief input to at least some of the parts that we'll look at, and probably the new things that people will show some results of today is related to numerical RTA, multiphase FMB, and fractional RTA. So I'll just give you a quick introduction on what this is. That's going to take 2 minutes. But just to make sure that the people who haven't done RTA for a while are on the same page, the way we kind of group flow regimes for these wells is into 3 buckets. Either infinite acting flow, which ends as a pressure transit that reach one of the reservoir boundaries, or if you're in the total opposite extreme of that, which is boundary dominated flow, then that starts, as you've seen, all of the reservoir boundaries. That's what we call tank-like depletion or pseudo-steady state. But in between here, we have what we call transitional flow. So that is the reason why we have, for instance, in many places we can have B factors higher than 1 for a very, very, very long time. And that's because of this flow regime right here. The second thing, just to remind ourselves, is what we can derive from RTA. It's an LFP parameter, and it's the contacted oil and gas in place. The LFP parameter is what we also call the A root K. It correlates with short-term CUMs, and it's to quantify it, you have to observe infinite acting linear flow. And if you want to quantify the oil or gas in place, we need to observe boundary dominated flow if you want to truly say what that number is. And if you're still infinite acting or transitional, this will of course be a lower estimate of what your EURs will eventually be and what your contacted pore volume is. So to try to put this into a little bit practical perspective for those of you who have done a little bit of it or a lot of it, we got this thing from Sam at Callan, who was with Diamondback before, and I thought it was a great way of kind of communicating kind of LFPs and OIPs in terms of IPs and EURs. So if you have high LFPs and high OIPs, you'll kind of be up in this quadrant right here where you have both high IPs and high EURs. But you can still have a high EUR even though IP is low. You'll just that just means that you have a low LFP and a high OIP, and vice versa. This will be a small completion. This will probably be what you would call an overstimulated. Last things. When it comes to numerical RTA, you'll see some diagnostic or some plots today, but the numerical RTA diagnostic plot, just for those who haven't seen it before, flat horizontal line indicates infinite acting linear flow. Deviation below this line represents boundary dominated or transitional flow, and the magnitude of the line itself indicates the LFP. This is from the work of Braden and James back in 2020. Then you will also see some work on multiphase FMB in a few of the presentations as well. That's a method that was developed by Leslie Thompson and Barry Ruddock, and that's a method that does not require roll perms, opposite contacted pore volume, does not care about geometry, but as all of these different flow material balance techniques, they assume boundary dominated flow. That makes sense because, like, okay, what is the goal of a flowing material balance? Well, it's to quantify the contacted pore volume. So if you haven't seen the whole tank yet, how can you quantify the contacted pore volume? So in those cases, you'll use it to bound your RTA results on the low side. The diagnostic plot is super simple. It's just some plots on a screen or on a graph, and you're trying to fit the straight line through the data, and the inverse of that slope is your pore volume. So this is a small OIP, big OIP, and even bigger OIP. Last thing you'll hear about is fractional RTA today. There you're going to hear the word delta. Delta is basically just this exponent right here on a rate normalized plot plotted log. So you just fit that in with the power law in Excel or in the software. That's from Jorge Acuna. That was at Chevron until very recently. What does this delta parameter mean? If your delta is 0.5, you're in infinite acting linear flow. If your delta parameter is 0, you're in boundary dominated flow. And if you have a delta parameter between 0 and 0.5, you are in transitional flow. I'm giving the word to Wade, just a little update on what's to come and what we're focusing on now in the near future. As you all know, we sent a little note on that. It's very different like this year, honestly, compared to last year, where we have an order of magnitude more users that use the software every day. As we have a big effort right now in just making sure that the software performance is upgraded. That deals with everything related to input and output of database operations. It's related to our API to make it run faster, that we're able to plot more data points on plots, especially if you deal with hourly data and you have like more than 20,000 call it timestamps, it becomes slow. And if more than that, it will even will even crash. So that's something we are working on. But that seems to be going very well. And just to give you an example of that, the numerical model, you would say 80% of that is just a database operation, uploading and downloading data into a database. And the simulation is like probably 20% of the time. So if if it runs for 5 seconds, 80% of it has nothing to do with even the simulation time. We're also making sure that we improve our DCA and type pool functionality. We've been doing kind of a big shift in terms of the product to make it more applicable to production engineers. We're including well test functionality later in the year. We already have this shower pressure group, a starting point for that. Some upgrades will come to that now very soon, getting in DFIT, and this very exciting DQI thing from Devon also later in the year. And this is, of course, in addition to everything else on both the multi-well numerical model. On the RTA side, in general, there's a tons of other upgrades there. So this is kind of a little bit beyond those efforts as well. So with that, I see I've all spent my 20 minutes, so I'll stop presenting and want to give the word to you, Wade, if you can both share your, there we go, excellent. And if you can share your screen as well, we should be ready to roll.
Right. See me? See my presentation? Hear me okay?
Yeah, sounds loud and clear. Thanks, boss.
All right. So my name is Wade Bostine. I'm with Camino Natural Resources. We're a private equity shop, currently mainly focused in the Anadarko Basin. We got about 130,000 acres in Anadarko, but we also have an asset in the Powder River. We've operated in the Permian. So we're constantly working with different companies, rolling up different companies, bringing their data into our systems. So we're constantly focused on data optimization, data organization, data structure, always trying to be as efficient as possible so we can spend as much time on analysis and operations. So today we're going to talk about bottom hole pressure automation, a little bit of what Matthias was alluding to there with the cloud-based updates and that sort of thing, and just how we're utilizing that and leveraging that data in our systems. So kind of the problem we were having, and that's been solved, and kind of Matthias alluded to, is that we have new wells coming online continually, require time to be built out and updated with production and Whitson on an hourly and daily basis. Bottom hole pressure data calculations and PPT data need to be incorporated into the company data warehouse and workflows multiple times a day to monitor new wells coming online and other analysis. So we don't want to waste a lot of time, having to update production every day, or especially with our hourly flowback is kind of the main one, where we have maybe 4 reports coming in on maybe 12 different wells every day. And we need to get that hourly data uploaded, those sand phase pressures calculated, and then get that data back down on our system so we can pipe it throughout the company and it can be used for analysis and operations. So we went with Conduit to kind of help us solve this problem. If you're unfamiliar with Conduit, they're a third-party company that kind of specializes in linking up to outside softwares, essentially building data warehouses for companies. So if you have IHS data, Enverus data, if you have daily production through Even or P2, Merrick, Combo Curve, any of these places, they can create links for you and bring that data down onto your servers so that you can leverage that data more efficiently throughout your company. So we reached out to them, got with Whitson, and tried to come up with a solution for this problem. So on the left here is just kind of a quick snapshot of kind of our data warehouse and all the data that Conduit has brought in for us. Like I mentioned, IHS, Merrick, Whitson, Enverus, and then as well as they also do custom programs. So for us to get this up and running, we had to have a couple things in place. One was the flowback loader that I kind of talked about that they put together for us. Is whenever a flowback report comes in from the field, from the flowback hands, it comes in via spreadsheet, via email, and that spreadsheet is automatically taken off the email and then uploaded into our SQL servers, into our databases, into our warehouse. So the other thing that we have in place is a Merrick API connection, which is essentially a connection to our daily production in the data warehouse. So once we have those two things in place, we have our hourly data on our SQL servers, we have our daily production on our SQL servers, we're able to move that data around the company as freely as we want and upload it to various platforms, including Whitson. So we also have all of our kind of company Aries databases on the right here. So as that data kind of comes into our data warehouse, we're able to move it around to all of our Aries databases and update them in kind of the same fashion on a daily basis, just so that we can be as efficient as possible and waste as little time as possible updating, uploading production, and spend more time on analysis and operations. So traditionally, we're kind of using another software that's kind of an older software that's a little bit outdated. It's just it's not the one that we want to go with in the future. We kind of want to. We're trying to get completely transitioned over to Whitson so that we don't have to even use that software at all anymore. You know, as all of y'all are aware, the Whitson customer service, the way they're building out their product is, you know, it definitely seems like the future to us, and so that's where we're trying to completely migrate to, so we don't have to deal with old stale softwares that don't really get updated or you know, don't respond as much as Whitson does. So like we said, Whitson already has the cloud in place for everybody to upload their daily production, but I guess originally, you know, we had these spreadsheet templates that we were using that were nice and they worked great. You know, just kind of upload your production into the spreadsheet, save it out there, and then drag and drop it, and your production's updated. And that worked fine and worked great. But of course, we always want it to be a little bit more seamless, and so that's why we have the cloud in place, and that's why we're utilizing that now. So for our solution, what we came up with was when a well is brought on flowback, we'll get that first hourly flowback report from the field. That flowback report gets loaded into our SQL database, and then that sets off the code checks to see, you know, any new wells brought online, and then that well hourly production is immediately uploaded into Whitson. So so we're able, and then in turn that sand phase pressures, bottom hole pressures are calculated and brought back onto our system so that we can quickly do our analysis on those wells and make real-time decisions with live bottom hole pressure data as far as choke openings go, and new well, an analysis on those new wells coming online. So once the well goes off flowback, the conduit SQL code recognizes that the well is no longer on flowback. It clears out the hourly production and replaces it with the daily production. So that hourly production is then archived into our data warehouse. So we have it for future analysis, future comparison, when looking at offset wells and comparing productivity and that sort of thing. We have all that data available to us in our data warehouse, and then it begins the daily production portion of the well's life. So, and of course, we have the bottom hole pressure calculations and PVT, Turner-Como rates, and all those are brought into our data warehouse. So that's kind of the really nice thing about the cloud and about Whitson and about their API that we have access to versus the previous software we were using, which was, if you ever went into the back end on some of these other ones, it was very difficult to get data out of, very confusing. It's just numerous tables, unorganized. You're kind of on your own, and they don't really offer a lot of support in that realm. So Whitson, of course, the customer service is amazing. So when they set this up, it's just very easy to use, very easy to access, you don't have to sift through endless tables trying to get your data out. Whatever you want, you know, they can kind of customize that for you and get you exactly what you need, which is really nice. So for instance, this top left table is just kind of a snapshot of a table of their bottom hole pressures that are coming down onto our servers. As you can see, they calculate all the bottom hole pressure methods. You don't just select one and that's your bottom hole pressure method. You have all of them available to you via the API, which is kind of nice. So you can kind of pick that on the back end and what you want to go with. And then they also have their Turner-Coleman rates out there without any further manipulation needed. And then of course the PVT data, all your saturation points, your initial GOR picks, all of that data, initial pressure picks, all of that data is also available via the API. So if you want to roll any of those maybe initial GORs into maybe some of your recovery factor work you're doing, or maybe some of your saturation pressures into some of your production surveillance tools, that's all available right there via the API. So once you have all the data in-house, you can kind of do whatever you want with it. So this is kind of some of the ways that we're leveraging that data. Like I've been talking about, the flowback data is kind of essential to everything we're doing here. When we're bringing new wells online, we're constantly monitoring them. We're constantly looking at the drawdown, trying to figure out when the next choke opening is going to be as we open these wells up in the most efficient manner. And then we also want to be able to compare to any other previous well that's been brought on flowback. So we want to be able to look at their drawdown versus this well's drawdown and be able to do comparisons there, and looking at productivity versus drawdown, productivity versus cumulative oil or gas, or just rate versus drawdown on a general basis. So Whitsun allows us to do that real time. Like I mentioned, we have reports coming in starting at 5 in the morning or 6 in the morning, and then every 6 hours after that, we have reports coming in on these new wells that are coming online. And as soon as that flowback data comes in, it's immediately uploaded into Whitsun, and then bottomhole pressures are calculated, and it's turned around quickly, so we can quickly get back to work, and we don't have to waste any time uploading that hourly flowback data. And then the PVT data in conjunction with the production data. I'm sure y'all have something similar to this going on. If you have access to the cloud, it's just kind of a production plot here. This is used in conjunction with the PVT data. So here you can see we have the two lines, the horizontal line and the vertical line there, kind of noting when the sand face pressure reached the critical point, the bubble point for this well. And you can see how accurately Whitsun's model is. PVT model for this basin was predicting those gas breakouts. So we use this a lot in this area of the field. And our production team would use it as well. Once you have the data there, we are able to pipe it to all the other departments in the company. So not everybody has to get on Whitsun. They can just access one of the tools that we have available out there, one of the databases, and they're able to go in there and look at what the well's doing from a bottom hole pressure standpoint. And they see the gas breakout and they're wondering what's going on. They can jump in here and say, oh, okay, that's exactly where Whitsun predicted that it would break out, is right there. And so that's been a big benefit for us to have. And then production can also help proactively prepare proper lift methods to continually optimally draw down the wells. So it's just been a big benefit for us, for the whole company, so that everybody has access to the data and just help us work more efficiently, waste less time on data, and more time on analysis and operations. So next steps for us, we'd like to get it to a place where once our well comes on flowback and we have that well in our system, that the property is automatically being created in Whitsun. So that's kind of what we'd like to get to next. And then we're going to work with some third-party SQL guys to help pick apart Rimbase for us, get our well bore data out of there, our production string data out of there, so that data can automatically also be uploaded into Whitsun. And we've already been working with Conduit to get some of our PVT properties uploaded into Whitsun, such as separator pressure and temperature and bottom hole temperature, so we don't have to go through and do that manually as well. So those are just some of the things that we're looking to do next. And overall, it's been great, as always, working with Whitsun and getting this up and running. So with that, I'll take any questions.
Awesome. I have a long list of questions here, and if there's anyone in the chat there that has any questions as well. Just the quick one that I had, this Rimbase data, is that just a place where you store like wellbore data? It's like in a WellView thing?
Exactly. It's like WellView. So it has all your production strings, directional surveys for mostly just proprietary data. So I know I put these next steps on there, and I don't think I've even reached out to y'all on that. So sorry if that caught you off guard, Matthias.
Great. Sounds great. I had a presentation before you. There was nothing here. I was a surprise, I guess. But there's a question from Matt here in the chat. This automatic wellbore configuration changes from WellView part of the current Whitsun API. So that is probably more of a question to me, I guess, Wade, or to us. And that's a great question. So all the external endpoints, they're very, very flexible, and they can take data from both WellView, Rimbase, or any of these. As long as it's a structured database, the API can read that data. I would say most of those, Matt, like most of the companies we work with, and that was why I asked about this Rimbase, is that they have a WellView database. So if you have a WellView kind of database with us, then that's probably, I would say probably 80-90% of the companies we work with that integrate that part, they will have that in WellView. And that's both for the Whitsun API and Snowflake. So that is by far the most common. And just for some historical context, actually, with Camino was actually the first company, I think a little bit less than 2 years ago, that we did do the API connection with. And before then, we had done like the whole spreadsheet thing for a while, and then we set up the API. In the beginning, the API, as you can imagine, was a little bit rinky-dink. It just did a few of the things that the minimum requirements basically. Now the Whitsun external API it's like its own product. It has a product manager with which many of you know with Jason. He's updating that documentation all the time. We have like very detailed documentation, both Swagger documentation and examples. And it has like a bi-weekly release schedule on the API side. So that's just a little bit of historical context there. Rohit has a question about how many times a day you're doing the syncing.
I believe we have it set up for, they can do it as often as you want, but we're doing it just when our flowback reports come in. So I think we have it set up for every 3 hours currently.
So every 3 hours. That's
time in between our flowback reports as well. So.
Yeah. And I see like there's no limitation on our end actually how often you would like to update it. I just see there's like a different preference depending on the company. That some companies does it once per week. Some companies does it every single day, and some companies does it every single day as well. And there's a follow-up question from Rohit there. Is there a way to automatically set up the PVT for every single well? The answer for that is yes. We do that quite a lot for most companies. What we do then, Rohit, is that we, at least for wells that is producing liquids, we basically just use the average GOR the first 30 days, or you can also suggest another type of logic. Jason has done that a billion times. So for you guys, that will at least provide a very good starting point, so that you'll have a good PVT pick for every single well as well. And so reach out to Jason on that if you need to do it, and the same goes for other companies as well. If I know some companies that are just putting in some dummy PVT data there for starters, but you can actually automate that piece as well. So at least you have a great starting point. Maybe you need to adjust the PVT a little bit, but in general, it should be fairly good. Awesome. Really appreciate this, Wade. Thanks for sharing this. I think this is a great starting point. This is call it a Multiphase RTA consortium. So the question might be, okay, well, why are we talking about bottomhole pressures? Well, everybody here knows that the bottomhole pressures is the most important ingredients together with rates into all of this type of work. And that's why we're spending a little bit of time on it. And it's also to kind of show what, how most companies are doing the bottomhole pressure calculations with the software now, so that when people that would like to do the RTA piece, they can always do that on evergreen type of analysis. So with that, we're switching gear a little bit, and thanks again, Wade. We're gonna go over to Mark from Diamondback. If you can both share screen and maybe I don't know if you have a camera there, Mark. It would be awesome to see your face as well. Mark joined Diamondback. Was it this summer, Mark, when you joined Diamondback?
I started July of 2021. So
yeah. It just happens very, times moves fast. But Mark
Yeah.
has been really fun to work with, and on the Diamondback side, they've been doing a lot of very impressive work. Mark has been really on the ball. He has a great intensity, so we make sure that we're on our toes all the time on the Whitson side.
Yeah, I try to keep y'all busy.
Yeah, exactly. That's what I like. But it also has made the tool much better, and kind of taking the ball from Wade there. This will probably cover a little bit of similar topics, but we're going to also cover this thing about calculation settings, which I think is very important for everybody in the call to be aware of, because that's more kind of a data issue, consistency choice that you need to be aware of, and that you probably need to make, which is, what should you actually do when you have bogus data. So with that, Mark, thanks for joining us today. I'll just leave the floor to you.
Okay, thank you. So hello everybody. Just brief introduction of myself. I'm Mark Watson. I am an associate reservoir engineer for Diamondback Energy. Diamondback is a Permian focused company, so we've got about 500,000 acres in the Delaware and Midland Basin combined. And during this presentation, please feel free to unmute your mics and ask questions during any parts of the presentation, or if you want in the chat, you can send a message there. But if you say something, I'll be able to hear it. So this is the Whitson Bottomhole pressure automation project that we've been working on for the past 6 months. So just before we start, just want to give you an outline of the presentation so you can formulate your questions now and or think about any questions, and we can get to those. So first, I'm going to go over why Diamondback is doing this project. Then a little bit of a Whitson, learning Whitson kind of discussion, and some SQL generation of how we got our data into Whitson, as well as speaking on the configuration settings that we've got, some configuration settings that we've got for calculations. Then doing a bottom hole pressure retrieval and correlation pick to determine how we pulled in or which correlation we pulled into our database. Then briefly touch on the API connection and automation process, and then do just a final product of what we'd like and some applications. So big question, why is Diamondback doing this project? It's really because our reservoir and our production team can make great use of it. The reservoir team can use it for analytical RTA, numerical RTA, numerical modeling, and our production department will definitely use it for bottom hole pressure surveillance, diagnostics, and nodal analysis. And I thank Wade because he showed that there's multiple things that we can do with the flowback data to determine choke size and opening settings. So that's something that I wrote down that hopefully we can implement in the future. So a little bit of my Whitson learning journey. So obviously everybody who's used Whitson's kind of got to learn the website in order to use it. So first we had to learn the website hierarchy. So the fields, the projects, then the wells. So it was pretty easy for Diamondback because we're only in the Permian Basin. So that cut down our fields to just one. But the projects, learning the company-wide projects versus private projects and who we can share and what we would like and make changes to those, and then going into the wells and learning the well settings. So then I learned the needed inputs for updating wells. So needed inputs such as lift types, tubing, casing, OD, ID, your flow paths and stuff like that. So the way I learned this was kind of doing individual uploads of wells. So not starting on the mass upload Excel sheet, but just doing one well at a time in Whitson, kind of just grabbing all the data from WellView very painstakingly and inserting into Whitson, and then grabbing the production data and putting it into Whitson. So I did this for about 20 wells and got a kind of a process of grabbing those wells easier and getting the needed inputs or the important inputs that go into Whitson. So then I started on the mass upload template, that Excel sheet that Wade showed. So I used that mass upload template to upload multiple wells at a time, and this helped me formulate the SQL that I'm using to upload those bulk sets of wells. So grabbing the production data, the wellbore data, the well header information, deviation survey. And first I started with just doing one well at a time. Then I kind of started adding on to it. So maybe I could do 5, maybe I could do 10. I think the most I did with that Excel was about all of our 2022 wells into a project. So that's a really great way to start your excuse me, upload process. And then after getting the upload down and understanding how it's done and making sure that's done all correctly, then I kind of dove into the upload and calculation settings. So determining whether we want to calculate from gauges on our ESPs or our flow paths for our gas lifts, whether we're flowing up the annulus, flowing up the tubing, or whether we're going to let Whitson decide, as well as gas lift configurations. I know Whitson's got those 3 settings for either you're flowing up your valve, or not, you're injecting into your valves, or you're injecting into your end of tubing, or you can let Whitson decide on that. So yeah, that's basically kind of how I learned Whitson for the first month or two. And doing that and doing the multi-well uploads, I kind of based my SQL generation for the mass upload template on the mass upload template. So you can see all these 4 steps here, which is the 4 tabs in that mass upload Excel sheet that Whitson provides. It's they're split into the 4 main sections. So you got your well header information with your well name, your unique identifier, which is our Aries prop num. So that's basically a primary key that is unique to each well. Your initial reservoir pressure, which here is set at a specific number, but now we've got pressure and temperature gradients for those running in our Python code. So just kind of grabbing the very simple, basic well header information and getting that into Whitson. So that was fairly simple on that first step. Then getting the production information, which is oil, gas, water, your dates, your pressures, tubing pressure, casing pressure, pump intake pressure, as well as your gas injection rates and your fluid levels. So this came with a little bit of a challenge. Sometimes we've got days, or sometimes our first prod date is not the first date that's in our SQL table. So in the beginning, we'd pull in months of just blank space because we don't have any production information or any information there. So we had to clean that up a little bit in order to make it more visually pleasing in Whitson to see. So our first production date is actually the first date in Whitson rather than getting months of blank data. So that wasn't too bad. And then step 3 was going onto the deviation survey. And although it's only measure depth, true vertical depth, and unique identifier, there are some challenges that comes with the deviation survey. If you've got, as if anybody's been a drilling engineer in this meeting, we understand that there are drilling problems and cause sidetracks. So if you're looking in well view and you've got multiple sidetracks, and you got to make sure that you're picking the correct sidetrack and picking the correct measure depth and TVD and linking those together properly. So that came with a little bit of a challenge, but what we did to get around this was just use the deviation surveys that we are uploading to, I believe, IHS and going to the Railroad Commission. So that made it a lot easier rather than going into well view and grabbing those measure depths and true vertical depths. But it is a backup for us. So if there is no IHS data, then we're going to grab that well-view data, wellbore deviation survey data, and upload it into Whitson. And then last, but definitely not least, the wellbore information. So I'd say that this is probably the most challenging portion of the SQL. You've got what we did was linked our Aries tables to our WellView tables, and this took quite a bit of time. The biggest issue is understanding the hierarchy of WellViews. So, you've got your ID well, and then your ID rec for your tubing string. But that ID rec, if you want to look at the tubing components to get your lift types and lift methods and depths of things, this tubing string now turns into an ID rec parent, and all the components turn into ID rec. So just linking that and understanding the hierarchy of WellView is a little bit challenging. But once you get it to work, you're able to, once you get to the automation process, just pull everything from WellView into a SQL table and upload it into Whitson. So we'd grab the tubing, depths, ID, OD, same for the casing, your lift methods. We looked at each component in each tubing string that we've got in the well and determined if there's an ESP pump in the name, that's ESP, or if there's valves and it's gas lift, or if there's a seating nipple, then it's a rod pump. So just grabbing a bunch of different things and using the run date as the date to start that tubing string in Whitson. So this is just an example, kind of to go over some configuration settings that we've got. So, we've got our ESP data right here in the beginning. So we've got in this black line, our pit data right here, right? And our bottom hole pressure correlations calculated by Whitson, blue, green, Hagen-Dorton bound, Beggs and Brill. And then you can see here, we switched to rod pump. And these are kind of the calculation settings that are set for this. So as you can see right here, rod pump compute when liquid level is 0. It's causing us to have very, very high bottom hole pressures calculated by Whitson because it's assuming, I believe, that the liquid level is 0, kind of like we're flowing the well, I suppose. So what we want to do in order to get around that is turn this off. I believe Friday we'll have that API running. So just turn this off, and you can see this is our custom bottom hole pressure line right here. So we're turning this off so that we can only calculate on days when there are liquid levels. So we don't have a lot of fluid levels here, but you can see where they are when you're using our Whitson's custom bottom hole pressure identifier. So this eliminates any really high incorrect calculated bottom hole pressures. So we also want to keep this off for ESPs, so we don't really know how much pressure the ESP is exerting on the fluid. So we want to keep that off so we don't get any incorrect, excuse me, so we don't get any incorrect bottom hole pressures pulled into our database. However, on the gas lift setting, we want to keep that on. There are instances where, excuse me, where we flow the well for a period of time in early life, I believe mostly in the Delaware. So we complete the well, run the string in with all the valves, flow the well for a little while, and then we set the compressor, get everything ready, and start pumping on, start injecting gas into the well to gas lift that well. I believe that's determined by the reservoir engineer or the production engineer. So we do keep that on when the gas lift rate is 0 because we want to calculate that early time flowing bottom hole pressure where there's no gas injection rate. And then right when we turn on that compressor and start injecting gas into the well, then we can start calculating that more accurately. So what we did to pick our correlation, so we ran a well, we've got a well, or gas lift well with a gauge at the bottom of it. So we inserted that into Whitson and downloaded the data from the Whitson website. And then what we did was, like I said, downloaded all these bottom hole pressure correlations and compared it to our gauge, and then calculated the error between the gauge and the correlation, and picked the lowest error correlation to put into our Aries SQL table. So, so what we found was that the Beggs and Brill for this well had the lowest error compared to all the others. We've got several wells that have pressure gauges at the end of tubing, so Beggs and Brill probably won't be the correlation that we pick because we've still got to go back in and calculate the errors for those wells. But that's kind of the process that we did to pick our bottom hole pressure correlation that we want to pull into our SQL database. So just a very basic overview of the API connection and automation process that we've got. I've been working with a data scientist on our team, Ping, and he's the one that's written most of this. So high level questions I probably won't be able to answer, but please feel free to ask because I can get to him and get back to y'all. But what we did, like I mentioned before, we had all of our data in our SQL databases. So we'd pull all of our production data, all of our well view data through SQL and throw it into Ping's Python code and use Whitson's API, their get, post, and put to upload all that data into Whitson. Then using their API, we trigger the bottom hole pressure calculation and get all that data and merge it into our Aries SQL database. So this is kind of the automation process that we've got. We've been speaking with our with our IT team in order to get the data to upload automatically with the Python code. So we should be having that within April, or then first couple weeks of April. But this is basically the API connection and automation process that Diamondback is using. And just some, the final product of what we want, some applications. What our main goal is to get bottom hole pressures for every well, every horizontal well every day. So currently we've got about 80% of our wells in Whitson, which is about 22. Yeah, it comes out to about 2,200 out of 2,800 wells. So all of our 2017 to 2023 wells are in Whitson. And what this is used for is by the reservoir department to do rate transient analysis and decline curve analysis. And our production department, they use it for artificial lift surveillance optimization as well as nodal analysis. So that's the presentation. I'd like to open the floor up to any questions that anybody may have. Thank you.
Awesome. Very, very good. Very good. I have a few questions on my list here. We just want to show maybe you mentioned this calculation settings, and I'll just share my screen real quick and show where people can access that in the front end. So if everyone sees my screen now, if you go to bottom hole pressure in the well data card right there, you just click calculation options up to the right, and then you can toggle these on and off, and that's basically just setting defaults. In the front end, you have to set these kind of in a well by well basis, but in the API, I think there's a release tomorrow that Mark referred to where these are possible to 100% automate as well. And that was some basically a feature request from Mark earlier this year, and I think it makes a lot of sense because you don't want your if this is feeding through other systems and other departments and whatnot, that you don't feed the production department with any bogus PHP data that doesn't make sense just because of the inputs. So very good addition to the software, Mark, and thanks for that feedback and for pushing us in that direction.
Thank you.
I have a question from Jorge here. Great presentation, Mark. What was the most efficient way to input the dates depending on the flow path? I.e., more than one input in the wellbore configuration, casing and analyst, tubing, etc.
So sorry, go ahead.
Yeah, so I don't know if you can also read the question maybe in the chat if you see it.
So is the flow path? Are you talking about gas lifts? Like if you switch from annular flow to tubing flow?
Yes, that's correct. Essentially, it's just like when you see the wellbore configuration, sometimes you just assume one just to see if it works, or at least that's what I'm learning. I'm going through the same workflow that you did, but I'm trying to get like what's the most efficient way to, when you have more than one flow path. Let's say we start with casing, then you go to tubing or annulus. Like, what was your workflow there?
So Whitson's got this feature which is kind of it's an unknown flow path, so you can switch between fairly simply, so that we don't have to, create a new tubing string and have like a run date for that. So we're just using that unknown setting on the flow path so that Whitson can determine which, based on pressures, which way or which flow path we're using.
So it's talking about this flow path option right here, which is just it's called unknown, and that allows you every day to based on the tubing and casing pressure to estimate your what the flow path is that day. But I still think kind of the question is valid if you're like if you first have casing here and then you have a second configuration and basically picking this date right here here that's associated with the change. So I'm a little bit unsure how you guys have done that, Mark, like the logic of picking that date, because I guess there could be maybe several different ways of doing that. If you flow through casing, put in a well on gas lift where you put in the tubing, but maybe there's no gas lift injection rates for a period of time. So maybe that's where you use unknown, maybe in association with that.
Yeah, so for picking for dates for all of our strings, what we're doing is going like I mentioned before, going into WellView and picking the first date of our workover. So we know that we shouldn't have any production data on that date. However, so we want to put that in there, which it won't hurt anything. But if you don't have your configuration in, when you do have production data, let's just say, you put, excuse me, you put a ESP and then you, so yeah, and you have production data before that, then you're going to lose out on that production data that the ESP string wasn't in. So we're just picking the start date of the workover job.
Awesome. With that, just because of time, we'll jump ahead. Thanks again, Mark. Really, really good. This was going to be kind of great input to some of the next talks. I'm going to assume now that Wade and Mark has provided us with beautiful bottom hole pressures that we can go ahead and use for nodal analysis and RTA. And that's where my good colleague Graham is going to share his screen and loop us through that. What I didn't mention in the intro that I probably should have mentioned is that for some of you that at least been working with us for some time, both Graham and also Teja that you'll see presenting later today are new faces at Whitson just the last couple of months. And I'm sure you can give a little bit more intro there, Graham, but I'll just leave the floor to you.
Awesome. Can you hear me okay and see my mouse moving, Matthias?
Yeah, perfect.
I just wanted to double check. I know Matt Yarnell had asked a question. I think you answered it. It was just about the automatic wellbore configuration changes. I think you answered it, but I wanted to double check before we moved on.
Yeah, that was about the changes from WellView.
Awesome.
Yeah.
Okay, thank you. Okay, so yeah, I mean, my titles of the talk is gas lift, but I'm actually going to be talking about a lot more than that. Just especially about kind of the direction that we're going with the nodal analysis, the wellbore optimization part of Whitson. And thank you for the introduction, Matthias. For anyone who doesn't know me, my name's Graham Helfrich, and you might know me back from FICET. So I started with FICET about 16 years ago, and I've been working with reservoir and production engineers and facilities engineers ever since. So the whole wellbore topic is really near and dear to my heart because my first week at FICET I spent with Louis Matar. If you don't know him, he's a big deal in the pressure transient analysis world, and he was schooling me all about IPRs and tubing performance curves. So if you wanted someone who's into wellbores at Whitson, consider me your guy. So I have never met someone who claims that they absolutely love their wellbore software, whether it be Virtual Well or Optimize, Perform, Prosper, all these different nodal tools. There always seems to be some important thing missing. They're hard to use, or the last time that those software ever got an update was back when I had a big full head of hair, like a decade ago, right? So this is really where Whitson comes in. So the wellbore capabilities that we have now are really just the beginnings, like Matthias mentioned at the very start. And so with your guidance, we're really trying to build a future-proof nodal analysis tool for the entire industry. So today I'm really going to briefly just show you what's new and what are some of our plans for the future to give you a wellbore software that you actually want to use. Okay. Now just skimming over quickly. I mean, a lot of the people today were talking about how they use Whitson kind of as a golden standard to do all the bottom hole pressure calculations. And coming from Harmony that I used for so long, there's some big differentiators that I noticed with Whitson that are leading to us being the golden standard for the bottom hole calcs. One of them, of course, is the pain of manually typing in tubing depth deviation surveys. It's such a big time waster. So we've already heard today how a lot of that is being automated. That's a huge deal. It's such a huge time saver, so you can focus on doing actual engineering work, right? The other thing is, we're used to, in some other software, fluid properties being correlations being used to determine the viscosity, compressibility. But as you know, in Whitson, instead we're using an equation of state model to give us more reliable bottom hole pressures in the wellbore, as well as everywhere else in the software. Pressure loss correlations, which one is right? In the past, you'd have to pick one and just hope for the best, but I really like that by default, Whitson is forcing you to see the entire range of possible bottom hole pressures from all the correlations, so you understand what that potential error is in your RTA work as well. Something that I've been craving for a long time is that whole ability to tune a pressure loss correlation to a gauge pressure, and Whitson's made it so easy. And of course, this means more reliable bottom hole pressures. We can use that tuned correlation on all of our wells that we don't have a gauge pressure on, knowing that it's more accurate. And ultimately, this means more reliable RTA results, right? You know, gas lift, you know, in the past, I've had to just put like a single valve depth in, but, you know, I found that Whitson is a lot more rigorous in terms of all the valve depths, open, close pressures, so we can honor where the gas is going in through history to give us that more accurate bottom hole pressure. And then finally, you know, the smoothing function, if we have noisy pressure data, it can be really tough once we get into the modeling side of things. Or like we saw today, if there's gaps in known pressure, instead of going into a table and trying to invent it, we can just do it visually. So, you know, I've only been with Whitson for under 2 months here, and I got to say the bottom hole pressure stuff is probably one of the things I'm most excited about. So that's kind of where we're at now. Let's look at what is brand new in the software that you have access to right now. Okay, so we're in Whitson software right now. Now, if we go down the left side, there might be a new part that you have not noticed before. It says Nodal analysis. Okay, so the process here is we simply pick a date from our history. I'm going to go to the most recent production date, like this, and an oil IPR curve is generated automatically. So the prerequisites to do this is you have to have done a flowing material balance analysis, and what that's going to do is it's going to have calculated your average reservoir pressure through the well's history, and that average reservoir pressure is going to basically be your y-intercept at this point in time for your IPR, and then the actual operating point at that selected date is going to be kind of your sample input for the Vogel IPR equation. So that's how your IPR is generated. Now we can also create the outflow curve or the tubing performance curve at that point in time. And we see for this particular well, we're kind of in a precarious place, meaning that our bottom hole pressure is so high, the well's going to die pretty soon. So this is where we need to start saying, you know, is gas lift going to help increase the rate for this well? You know, how do I want to design and plan the gas lift? And that's exactly what we're going to do now. So I'm going to start with just like something simple, like a poor boy gas lift here, basically injecting at the end of tubing. And maybe we start with 100,000 cubic feet per day injection. We'll create a new outflow curve here for that. Okay, so we see that we're going from our kind of precarious here, right here at 400 barrels per day up to about 640 barrels per day, injecting at 100,000 barrels a day. Great, that's something, a sensitivity we want to try, right? So I'm going to save this case. Now I want to try some other sensitivities, right? What about 200,000 cubic feet per day? Create a new outflow curve, and we can compare it against the first one here. So 100, injecting at 100, injecting at 200. We'll save this. Maybe we'll go up to 500, injecting that much. Now at some point, we're going to kind of get diminishing returns here. Let's try that again. There we go. So here's our 500 injection case. Now, so this is just considering, you know, poor boy style gas injection. What if we want something a little bit more rigorous? Well, as you know, we can go in and specify our valve depths, our valve open close pressure. So this is something where we can apply some more detail to see what our rate would be at different injection rates and different injection pressures. So what if we do that and we inject, you know, at 1,000 pounds casing pressure, create our new tubing performance curve, and this is what we're seeing here. So, you know, with this, you know, more where we enter the valve depths, this tubing performance curve is actually predicting which condition along the annulus which valve is going to be opening and where that gas is going to be going in to predict the bottom hole pressure and then the tubing performance curve. So this is all available right now, and again, it's built into your Whitson software. It's available, and I think it's really practical. It's really quick and easy. But what I really want to focus on is where we're going this year and into the future. Okay. Okay. So a lot of what I'm showing you is really feedback that we've received from you. It's really here to solve specific problems. Let's look what I'm talking about here. So whenever we make a numerical model and we run a forecast on it in Whitson, right now we have to assign a bottom-hole flowing pressure constraint to create the rate forecast from the numerical model. It's really tough to kind of guess at that bottom-hole pressure sometimes. So what's coming based on popular demand is instead the ability to put a wellhead pressure or tubing head pressure constraint. And as a result, the bottom-hole pressure will simply be calculated and estimated to produce the rate from the numerical model. This is very high on the priority list. It makes a lot of sense to use something that's a bit more known as a pressure constraint, being the wellhead pressure, than a bottom hole pressure as an input. Okay. Now, an evolution of that's going to be coming in a little bit later is to start planning and scheduling artificial lift as part of your numerical model forecast. So saying, if I install an ESP at this depth, at this time, with this intake pressure, what not only will my instantaneous rate response be, but what will my long-term cum difference be for that method of artificial lift, all driven by the numerical model. And then if we want to schedule some gas lift, again, the same kind of details I showed you in terms of different valve depths, injection pressures, predicting both that instantaneous drop in pressure and of course the rate response now and into the future. So I think this is going to be really a game changer in terms of just doing long-term planning for production optimization, really based off the numerical model as the replacement to an IPR curve. The other thing, of course, is right now we do the oil IPR tubing performance curves. Next is going to be coming, a gas, right? Gas inflow and outflow curve. So we'll be using the Folkheimer method for the IPR curve initially. We might do some more complicated ones later. And of course, liquid loading is, of course, a big deal with gas wells. So by default, we'll show you what the critical lift rate will be for your outflow curve. You'll be able to do all kinds of sensitivities on different wellhead pressures, different tubing sizes, things like that. On the topic of liquid loading, of course, an IPR curve will tell us what rate the well will liquid load, but it won't tell us when in time will liquid load. So that's where the numerical model comes in. So if we have a gas reservoir model, we'll create a gas rate forecast, and we'll show you when in time the well will liquid load. And of course, then you can start to schedule things like compression, tubing changes to, of course, delay that liquid loading into the future. By the way, I'd really welcome any thoughts on after a well has liquid loaded. We know that there's an extra delta P in the wellbore, but it's really tough to estimate or calculate what is the delta P caused by liquid loading. So if there's any papers or anything, we'd like to do that just so we can try to apply and predict the pressure loss and then therefore the rate loss from a liquid loaded well, just to quantify it. Something else is, of course, Whitson does a great job with the gas lift details, predicting the bottom hole pressures. But something that we don't do right now, we don't report which of these valves is actually active and open through time, right? It's happening in the background. We're not reporting it. So it'd be nice to know which of these valves is open through time, and that's what's going to, be coming in the future. So if we're doing a historical bottom hole pressure calculation using our gas lift injection rates, we'll also be able to report through time which valves are open. So this will apply both to historical bottom hole pressure calculations, as well as if we're doing a tubing performance curve with gas lift, we want to be able to report which valve is active and open as well at the different depths along the wellbore. And then again, this reporting of gas lift activity, different depths, which valves is open, will also apply to when we're doing future scenarios based on a numerical forecast where we schedule gas lift in the future. Now, does anyone have a guess what this other feature is going to be related to? I'll give a couple seconds for anyone to chime in. I'm sure you do. Okay, chokes. So, we're really going to hopefully be implementing both wellhead chokes and bottom hole chokes to predict pressure loss through them. Now, for a bottom hole choke, it seems like it would make a lot of sense to consider liquid loading as well, because, upstream of the choke, we've got high pressure, and then downstream of the choke, we have a lot lower pressure. And so the velocities are changing. So, I think we'll be considering, liquid loading, critical velocities needed to lift both kinds of liquids, water and condensate, on both sides of the choke. So this will be coming, and hopefully it's it's something you guys want. So something really minor as well is using different pressure sources to calculate bottom hole pressures. So if we're flowing up the tubing and we have a tubing head pressure, we can of course use that tubing head pressure to calculate the bottom hole pressure, right? But what if we're flowing up the tubing, but we want to use the quiet side pressure, meaning the casing or the annulus, to be the pressure source to do the bottom hole calculation? That's something that we can't do at this moment, but it's going to be coming. So it's really just having the option to use the flowing or non-flowing side to perform bottom hole pressure calculations through time. So I think the most important thing here is you're going to get all of these wellbore improvements, a lot more, just as part of your annual partnership with Whitson. You don't need to buy extra wellbore software. It's going to be built into the same platform, the same licensing. And this is really why I like to use the word future-proof. I think, you guys are already partnered with Whitson, and I think you've got a great future-proof relationship in terms of RTA, bottom hole pressure, nodal analysis, decline type well, and even DFIT functionality going forwards. So really, this is my talk today is really just to give you this preview. I want to know, are we on the right track? Are there important things that we're missing that you want for wellbore optimization? Everything we do is really driven by you. So I'll just shut up and open the floor to questions here.
Awesome, thanks, Graham. Yeah, I'll just fire with a question right away from Jeff here. Does the software support any of the modified critical gas calculations for deviation or strictly Turner/Coleman? A paper that comes to mind is SB, I guess 115567 from 2008, but I'm sure there's been updated studies out there since then. And you can answer this, Graham. I think I can answer it as well. But
yeah, I think we have the same answers. It's not right now. Right now we just started with Coleman and Turner. I mean, we'll check out that. I'll check out that paper. I'm curious what problems it solves. I'm sure it's a very specific problem, but so we'll check that out, right?
Yeah, 100%. And and these kind of feedbacks like this, if you guys have experience with this from case studies or whatever, that's something that's worked much better than, for instance, Turner and Coleman, reach out to us and we'll make sure to account for that. Here the questions are coming in. Graham, always been a fan of your educational videos. Can we expect a series of videos from you related to IPRs and examples? It's from my very good friend Saul. Graham, I've been asking him about the same thing, so that's good.
Yeah, I've only been here 2 months, so I'm trying to delay the expectation for Matthias before I start churning out these videos. But yeah, I think maybe what I would start with is kind of like what I showed today. I think I'll just make a recording of that and put it online soon, and then it's really just thinking about different case studies to illustrate. I feel like I'm in the position where I'm learning something new about Whitson software every day. I'm like, oh, I didn't know it could do that. That's awesome, right? So I think I just need to capture that because I think other people probably don't know about all these different functionalities that I'm learning as well. So yes, I'm working on it.
And then we have a question, is it planned to integrate surface choke modeling with wellbore VLP calculations?
I think that would make sense. Yeah.
Yeah, it makes sense. It sounds like it's not. We haven't thought about it yet, but it's a great feedback. So it's something for us to think about. 100%. What we're going to do now is we're going to take a little break, but I need some help from you all to be kind of strict on time. A little coffee break. We're going to make that 7 minutes, and we need to start 9:30 sharp Houston time, 8:30 Calgary time. Okay. So just hope everybody can help with that. And then after that, we'll start with my very good friend John's presentation. Really excited about that. It's going to kind of take on a little bit of the things that Graham talked about, making sure why we introduced this nodal analysis feature in the first place. Yeah, so we'll be back here in 6 minutes now. Okay. So I think we'll get started again. Next up on the list here, as I mentioned, is John from Devon. John, are you able to hear, or the sound, is it coming through okay? There we go.
Slides sounds great, Matthias.
Yeah, perfect. You're loud and clear. So just for everybody in the audience here, I didn't know actually, John, last until maybe August, which was the time I think we were introduced to you and working with kind of you and your team there at Devon. We'd done a lot of other things with Devon until that point, and then we kind of started the whole initiative of automating bottomhole pressures, etc. And through that was kind of where this great suggestion from John on should we maybe include some nodal analysis in the software, and I think that turned out pretty good. It's of course a starting point. We have a lot of homework that Graham just mentioned on where we're going. And I think you also have some good ideas for that. So with that, John, I'll just leave the floor to you.
Perfect. Thanks, sir. Hey, everybody. Appreciate the chance to get to address the group. So thanks to Matthias and the folks at Whitson for putting this on. I guess just a quick background on me. Again, my name is John Pratt. I'm an operations production engineer at Devon. I've worked in, kind of started at a major. I worked in facilities engineering, offshore, some more midstream type assets before making my way over to Devon. I've been working in really the production space for most of my time here. I bounced around a little bit from Permian Basin up to the Powder River Basin, and here most recently in the Eagle Ford and our Mid-Con asset in the Stack Basin. As far as Devon's concerned, again, we have operations kind of across the U.S. and most of your major oil shale plays. So we've got operations in the Powder River Basin, Williston Basin, obviously the Permian, as well as the Eagle Ford and Mid-Con. So as far as what I'm going to be covering, it's really just some of the background and the story behind the nodal analysis tool that Graham was showing. So I guess just to get kicked off, kind of in general, kind of how this came to be. So in the fourth quarter of last year, we were working with Matthias and Jason and the team over at Whitson to automate a lot of our daily bottomhole pressure calculations. We've had a couple of really good presentations already, kind of talking through some other company processes and how they approach that problem. So I won't get into too much detail. Again, we've got a similar issue as really the rest of the folks here, probably on the phone, and certainly those two that did present. We've got data in a number of databases. When you think about nodal analysis calculations or flowing bottomhole pressure calculations, you need to create a wellbore configuration and then get in production and pressure data. So the way we were approaching that problem is using Snowflake Share. So what we've done internally is go out and grab all those different sources of data that we need, from production data, wellbore data, gas lift, valve, PSO, PSC, set depth information. We keep track of artificial lift method, if we're flowing tubing, casing, or annular flow. Combine all that into a single table, push that to Whitson, where they're able to actually do their thing, run the numbers, and then we receive data back from them with the results from those bottomhole pressure calculations. So there on the right-hand side, we've kind of got the outputs of this jumble of databases that's all feeding ultimately into a Snowflake table that we're able to push across. So that top graph is going to be a bottomhole pressure graph that you would see in Whitson software. A lot of times what we do struggle with here at Devon, especially in the production and operation space, we've got a lot of tools, and sometimes it feels like we might have too many tools. Different ways to visualize data. Most of our production engineers will have anywhere from 150 to 350, upwards of 500 wells maybe, that we're responsible for on a day-to-day basis. So being able to quickly access and consume data is super important to us. So we did want to have the ability to bring that information back and visualize that in some of our platforms that our folks around here are more used to seeing. That graph happens to be from Seek, but we also use Pi, which is an Aviva product. So here in the fourth quarter, again, we're working directly with Jason and team, Jason, Matthias, and the Whitson team to set up these tables and make sure the share is working for us correctly. And suggestion was made from our side, hey, this is all the information that we need that we put in anytime we're going to perform nodal analysis. So in general, nodal analysis it's kind of a pain to perform. I think Graham hit on some of the pain points already. A lot of the software is old. We happen to use, looks like it might just be written in Excel, VB code in Excel. So anyway, it hadn't really been updated in a long period of time. And there's a time component to it as well. So it's a manual entry process that has to be done anytime we're going to actually go out and execute that analysis work. So what we suggested was, hey, we're basically creating the well bores. We're doing everything but grabbing a reservoir pressure and inputting a new tubing configuration. As Graham already mentioned, with their flowing material balance calculations, Whitson's solving that first problem for us, that reservoir pressure. And then the other one is just an input that we would need to create, which is the alternate tubing configuration that we would want to be installing into the well. All right, so fast forward to today, the guys really did a quick turnaround and had a product out that I think is super helpful. I've gotten to use it a little bit, and I think it's valuable and will probably be something we start to use more and more in the future. I would say I had conversations with Matthias, Steen, and Mo with, I don't know, within a month probably of actually bringing that up. It might have been 2 weeks after kind of bringing this up as an idea and a suggestion. So for those of you on the phone that maybe haven't had as much interaction with the Whitson guys, that they will take suggestions and ideas seriously and act on them very, very quickly. So if you have ideas, things that you want to see, I would just encourage you all to address the team directly and see what they can do. All right, so let's talk through just an example well, a little bit of background, and then we'll pull up the tool and do a quick live demonstration similar to what Graham just kind of walked us through. So we've got a well that's a Eagle Ford producer. Here, let's turn on the... Okay, so just kind of walking through the well production history. We brought this particular well online in January of 2012. And just to quickly orient everybody, we're going to have gas and oil over here on the left-hand axis. And then on the right-hand side, we're going to have our pressures. So we'll have tubing and casing pressure in gray. And then this kind of brownish line, fittingly, not accidentally actually, but that's the Hagedorn in brown. So anyway, that's going to be over here on the right-hand axis. So we brought this well online in early 2012. We flowed up casing until tubing was installed in the fourth quarter of 2012, right around this time frame. You can see here we get into some periods where production's offline. We see quite a bit of abnormal production decline. The notes get a little bit spotty in this time frame. This was kind of before the asset was acquired by Devon, so it's a little bit difficult to follow exactly what happens. But somewhere in here, the tubing was pulled, the well was bashed by offset activity, and you can see an impact to that production performance. So essentially, we bring the well back online here in 2014, and we're flowing up casing at that point. From a bottom hole pressure standpoint, we're still flowing up around 4,000 PSI as our calculated bottom hole pressure. Again, using that Hagedorn and Brown method, but really all the flow correlations had it somewhere in that same neighborhood. All right, so we ran a flowing pressure survey on November 22nd of last year just to confirm the pressure that we were seeing. As you can see, that the gauge pressure that we actually measured was quite a bit higher than the flowing pressure calculation. Again, this ties back into some of what's already been mentioned, that calculating bottom hole pressure when you're below critical velocity and don't have a real good measurement of where fluid level is challenging. So if anyone has ideas for how to improve that, I'm sure the Whitson folks would certainly be happy to hear those and act on them. But in this case, we have a flowing pressure of roughly 6,100 PSI. Following that, obviously, we're going to go through do work with a gas lift vendor. We're going to create a gas lift design working with that vendor. And then we want to actually go through and run nodal analysis so we can determine the uplift and what the workover economics are. We know our costs. We need to have some kind of estimate of what we think the production uplift is going to be so that we can determine if this proactive work is something that we want to pursue or not pursue. So with that, let's go ahead and switch over to Whitson. Okay, awesome. So I've got the well pulled up here, and we've got the same nodal analysis option selected, some of the same data that you see that Graham had pulled up. So here we've got a well. This is the first day of production. We can click through and pick whatever day we happen to be interested in. So if we were interested earlier in life, we could see this information. But really for our example here, we care about a specific day, and that's going to be the day that we ran that bottom hole pressure survey. So we'll pull up the data from November 22nd of last year, and here we can see the various rates and information that we need to see. So the well made 10 barrels of oil a day, roughly 37 MCF of gas, and you can see our pressures were right around 600 pounds. We know in general, this well, especially with where we're operating at, it tends to slug quite a bit. So the rates kind of fluctuate all over the place. Again, we're trying to determine if this is a good workover for us. So we'll be conservative. Flow rates tend to fluctuate between 5 to 10 barrels of oil a day. So we'll go ahead and just say it's going to make roughly 6 barrels of fluid a day. Our typical water oil ratio is about 0.2. We'll make a barrel of a pretty low water cut, but it's not abnormal for us to see about a barrel of water per 5 barrels of oil. And then on their gas oil ratio, again, it's calculating based off of this day of production. It happened to be high that day. Generally, we're somewhere in the 6,500 to 7,500 range. So we'll just plug in 7,000 for this particular case. All right, so now we've gone through and kind of generated all the necessary information for what the well is doing today. Let's go down and focus in on this new well configuration option. All right, so the current well configuration, this data is all coming across from the data that's pushed into Whitson via Snowflake. So this is not a manual entry on our end. It's integrated on the backside and actually talking from one portion of the tool to another. So we've got our casing data in here. Obviously, there's no tubing installed because we're flowing up the casing. So for our new well configuration, we're going to put in the tubing string data that we've designed, plugged in our gas lift valve data that we've designed. We are open-ended, so we'll have an injection point down around the end of our tubing. Go ahead and save. One last thing. So injection rate, 350 MCF a day, makes sense for 2 3/8 inch tubing. Typically, we'll operate somewhere around 150 PSI on the tubing and 650-ish PSI on the casing whenever we're fully unloaded and injecting on bottom. So now we've gone through, run all the numbers that we need to. We've updated the productivity index data. We're going to run a case. Let's just assume that we don't have that flowing pressure survey. So we're going to use the information that we've got from the calculations and the bottom hole pressure and flowing material balance, and we'll go ahead and create this system curve. All right, so the blue dashed line is going to be the forecasted system curve. So this is where, just based off the inputs that we fed this model, where we would expect to be operating at. And as you can see, we come pretty close to where the actual operating point is. More importantly, for our incremental economics case, you can see forecasted new operating point is going to be down at 30 barrels of liquid a day at a bottom hole pressure of 522 PSI. That makes sense with what we see in other wells that we've got tubing installed and they're unloaded and injecting around the end of our tubing. So qualitatively, the numbers that we're seeing make sense. So what the forecast here is that we would expect to see an uplift of oil somewhere in the 20 barrels a day range. So this is likely a project that we would want to go out and execute. Just one specific item here. So we did measure our bottom hole pressure. So since we know what that number actually is, we can put that in. So in this instance, it was roughly 6,080 PSI. So we'll need to go ahead and up our reservoir pressure. Obviously, from a physical standpoint, the reservoir pressure can't be less than that bottom hole pressure. Again, we know it's kind of challenging to estimate this number, but we'll just go ahead and assume it's relatively close. The delta between flowing bottom hole pressure and reservoir pressure was somewhere in the 200 to 350 range. So we'll just keep that and assume it's going to be a 6,500 PSI reservoir pressure. Go ahead and calculate. And you can see now we've got another simulation. Only here we're saying our uplift could be as much as 63 barrels of liquid per day. So we could see 40 to 50 barrels of oil uplift per day, especially initially as we've got some high reservoir pressure. And obviously we'd expect that to come down as we deplete the near wellbore pressure and see that reservoir pressure come down. So all in all, it's a very quick way for us to be able to actually go in and perform this nodal analysis. Historically, we would have had to have gone in, manually created the wellbore, manually input production data, manually put in things like gravity, water gravity, oil gravity, gas gravity. So it's just a time saver for a nodal analysis workflow that we don't necessarily do a ton in the production operation space. Largely because it just takes so much time. But in general, times where we're looking at either installing tubing, maybe considering annular gas lift versus conventional gas lift, those types of decisions where we need to have some kind of idea of what the well could produce with various forms of artificial lift, various operating methods. This is going to help us quite a bit to be able to run these numbers more quickly. Just one other thing I would throw out there and mention before taking any questions. We do see one thing that I would love to see added, and if you guys are on board with this and would like to see this as well, I'd encourage y'all to reach out to Matthias and the folks on the Whitson side. We would like to see more of the critical velocities through the curve or through the entire wellbore configuration. The critical velocities that are being calculated and reported right now are using surface conditions. It just makes sense to us that since we've got an estimate of pressure and temperature kind of throughout the wellbore, it would be good to see that critical velocity at a minimum at the bottom hole conditions and there along the lateral as well, or along the wellbore as well. Just to give us an idea of if we actually are crossing over a threshold and potentially loading up at some point in the tubing, even though we might show calculating at surface conditions, we might not have an issue with loading. If you actually break it down and look down the wellbore, there's always a potential that you're crossing over that threshold and actually are seeing liquid loading in the wellbore itself. So with that, I'll go ahead and quit sharing and take any questions that you got.
Awesome. Great, John. It's always when you are showing the software, it's always fun to see people. I can't remember that we even had any sessions for you to go through the features. That was great to see that how self-sufficient you were. So that makes me happy. Graham has a question. Do you want to unmute, Graham?
Yeah. Can you hear me?
Yeah.
Okay. Hey, John. Thank you. So just to your last point about, instead of using a tubing head pressure to predict, critical velocities along the wellbore, like in the case where you have a measured bottom hole pressure, it may tell a different story, right, in terms of those velocities in the tubing. I think, is that what you're saying?
Yeah, that's correct. I might do this outside of this meeting. I can send you a couple of screenshots from our other software where we've got cases where we'll using that surface condition, it'll show that you're unloaded at say 350 MCF a day or 250 MCF a day of injection. But when you actually look down the wellbore, you actually cross that threshold and you're in the loading condition further down in the wellbore. So again, if you're calculating it at your bottom hole condition, you'll actually see something different sometimes with those Turner and Coleman calculations than if you're just relying on that surface.
Got it. Okay, good. Thank you. Yeah, let's talk more about that. Sounds great.
Yeah, be interesting to hear if anyone else on the phone or has seen that same type of calculation kind of play out on their end, but that's certainly something we've seen a couple times.
Awesome. Can you comment on just like you mentioned that it would take some time and whatnot if you let's say you wanted to do exactly what you did now, if you had to move all the wellbore configs over to another tool and stuff, can you say like on average ballpark how much time you would save to not do that piece by just doing it in the same tool as where you have your wellbores and the production data?
Yeah, I think conservatively you're looking at probably 15 to 30 minutes on the setup side, probably, maybe a little bit less than that if you're in the software on a regular basis. But again, at least here at Devon, nodal analysis is not something we perform frequently. We tend to kind of only use that as needed. So when we're actually going through and performing those calculations, it can take a little bit of time to actually go in and grab that data. Depending on how friendly your software is, sometimes loading in the deviation surveys can be a challenge. Exporting it to a CSV and then copy pasting in the whole thing sucks, and it certainly does take time as well.
Awesome. No, that's really good. I just see on time I have a few other things, but I think we can follow up on that later, John. Really appreciated all the feedback and all the meetings and help the last few quarters and months. I'm looking forward to getting more such that we can make the tool even better. And that goes for the whole group here. As John mentioned, some of you guys we talk with almost every single day. And if you have ideas, if you have requests, if you have feedback, feel free to reach us out to us at any time. And we in many cases, we actually have a lot of the user feedback in the backlog already, but many times, like with John here, Mark had something on the calculation settings. There's a ton of this that we get in every single day that just makes the software better, and that's our only goal, is to make sure that we get the software better and that we include things that you guys want, not things that I want or that Venkata or Graham and Mo, but people that actually use these techniques on a day-to-day basis.
Thanks,
awesome.
Matthias. And I think I forgot to mention this, but I'm pretty sure y'all made that unknown flow configuration just based off our feedback as we were kind of going through that, automating the data transfer into Snowflake. So
yeah, exactly.
Yeah.
So that was also another thing that kind of came out of this. I think I probably mentioned it in a by sentence a little bit earlier, but that's very helpful in cases where you load like thousands and thousands of wells like you guys at Devon does, where the flow path might be unknown on a daily basis. So just being able to set it and let the software automatically pick what it thinks makes sense based on some set rules, that seems to work well. But thanks again, John, really appreciated. We're going to jump gears a little bit to my very good friend and our COO, Mo, the Dahook, as we like to call him internally. I can hear your voice, I think now, Mo. Can you?
Yeah. Can you hear me?
Yeah, sounds great. Beautiful background. Tell everybody what the background is, what town that is, and you can get started. Sounds good.
Yeah, both actually my camera background and my background that you see in the presentation, they both correspond to Trondheim in Norway. It's a city in the middle of Norway, a little bit north of the capital, Oslo. And if you look carefully through my window, you'll see that there's still some good amounts of snow outside. So that's where I'm sitting right now. That's where I work for at least most of the year from Norway. Anyways, so the title of my presentation sounds a little bit like a challenge, 10 case studies in 10 minutes. But hopefully it's just some teasers. Actually, is what I would like to call it. It's just to show you some of the things that some of you actually have been doing with the software, and just to share it very quickly with the entire audience here in the GIP. So my name is Mohammed, but as you probably have interacted with me, if not, then everyone calls me Mo. So you just call me Mo. I do a lot of things related to the software together with Matthias and the rest of the software team. But my title officially is the COO, because I also do a bunch of other things related to the company. I'm gonna, as I said, just go quickly through these 10 case studies. Don't feel wrong or bad if there's something here that's not completely clear, because it's as I said, a little bit of a challenge to try to go and cover 10 case studies in 10 minutes. I'm just going to try to give you enough of each of the case studies so that if this is something that you're interested in, then you can reach us through support@whitson.com or contact Matthias or myself, and then we'll make sure to show you how this is done in more detail. Okay. So the first of those case studies is related to Matthias. Can you see the top of my screen? I see something here on the.
Yeah, we see it.
There you go. Yeah. The first one is going to be related to evaluating refracts using Whitson Plus. And as you all know, basically when you're working with refracts, you're going to have basically a well that has been in production for some time, and then eventually you decide that there's some likely some parts of that rock that are still unstimulated and that you would like to contact with a refrac. And this is actually an example from Devon well in the Eagle Ford, where you see that there's a refrac occurring later in time. And after that refrac has come, then you see a significant improvement in at least the production, the rate versus cum here. Generally, what happens is that those refracts happen later in time when you've already had the bottomhole pressure gone below your saturation pressure. So that means that you have actually quite a bit of multiphase flow happening in the reservoir. And that's why using a method like the multiphase flow and material balance would make sense, because there you're accounting for all the PVT and all the multiphase effects that are happening in the reservoir. So what we do is that, or what we did with together with Devon, is that we took and tried to use this data in the flow and material balance feature in Whitson Plus. And with that, we basically get what you see here on the left. You get two slopes. And for those of you that are not familiar with the flow and material balance, each of the slopes basically represents contacted pore volume. So if I find this upper slope here, that is the data pre-refrac, that corresponds to a contacted pore volume of about 1 million barrels. And the slope after the refrac corresponds actually to almost twice that volume. And that's something that you can very easily do in Whitson Plus. So in this case, for example, you get twice the contacted pore volume. And for those of you that are interested in this also, I think we're writing a paper on this together with Devon that's coming for UTEC 2023. And in that paper, I think it's 46, yeah, it says here 46 cases that are going to be shown where the refracts have been applied and where Whitson Plus has been used. The flow material balance methodology in Whitson Plus has been used to do that. Okay. The second thing I wanted to talk about is using Whitson Plus to compare productivity between different wells. And what I'm showing here is basically an example from the diagnostic plot where you can plot multiple wells, plot basically the rate normalized pressure or pressure normalized rate versus material balance time or versus real time. And that you can do for all the wells that you have in your project, just to be able to compare the productivity for the different wells, because we know that each well might have a different drawdown history, might have a different completion, et cetera, et cetera. The one thing that is interesting about Whitson Plus is that you don't only get to do that on oil and gas and water rates. If you want to do it here, the example shown here is on oil rates for a set of wells from the Eagle Ford, but you can also do it on total liquid and also total reservoir rates. So we use the PVT that you have input to convert from your surface rates to reservoir rates. So you can do this analysis on reservoir rates, and many of you have been doing that and found some very interesting results out of this. Okay, so in this example, you see the increasing productivity, how the productivity for the different wells can be compared, at least in a consistent manner, when it comes to these rate normalized pressures or pressure normalized rates. Now, one of the recent features that we have introduced into the software, or the most recent ones, is this CPG method. And many of you are familiar with this. Basically, CPG quantifies the pressure interference between between wells that you might be observing in your field. And the way it works is that you basically have it only requires bottom hole pressures as input. So this is an actual example that you see here from the Permian Basin. And you only need pressures. And what we do is that we look at the pressures in a monitoring well before and after a well that is a neighboring well is put in production. Okay, so this is the pressure trend of the monitoring well, and the vertical line here is something that you'll be able to move in Whitson Plus. And that will show you basically, that will determine, you will decide when the neighboring well was put in production. Okay, and then the trend of the pressure before and after the neighboring well was put in production is what we're going to use to calculate the CPG in Whitson Plus. And if you get this data into Whitson Plus, loaded into Whitson Plus, you get something like this, where you basically get a CPG plot like the one shown in the upper right here. The one at the bottom left is the derivatives that are used to calculate the CPG. And then this basically, for example, gives you a CPG value of 0.5. And what does that mean? Well, depending on the CPG value, you can determine quantitatively or qualitatively as well the level of pressure pressure interference that you have. So in 0.5 is basically in the border between weak interference and moderate interference. Okay. So that's this is a feature that a lot of you have been testing. One quick comment about this feature: we've just made an update of how the pressure, the derivative is calculated actually with an integral method, and that for those of you that were using the feature maybe right when it came out, you should give it a try. I think in the next couple of days there will be an update with the derivative being calculated with an integral method, and that helps a lot with smoothing this data. Okay. The fourth case study is related to PVT property mapping. Basically, 90% of you that are subscribers to Whitson Plus are also part of our PVT equation of state model JIPs. And with those, what we can do is basically go into a field, into a basin, into a whole area that we would like to decide, and we can estimate PVT properties in Whitson Plus based on very limited amounts of data. So for example, we just have the GOR for each well. We don't have anything else. And with just the GOR, with a map of how the GOR looks like, then we can generate a map of different properties. The ones here are shown the viscosities. You can generate phase envelopes. You can generate formation volume factors versus location. You can also generate, for example, saturation pressures. This is an example that was presented in a previous knowledge sharing session by some of our colleagues from CPG working in the Duvernay. Okay. The fifth case study is already covered quite a lot, so I'm not going to spend much time on that. That's the automatic calculation of bottom hole pressures. There's no need to continue discussing that, but most of you already are actually doing this, so that's good. Case study number 6 is actually something that some of you, I think, are not aware that we have available in the software, and that's the possibility of modeling multiple layers in the numerical model. What's nice about Whitson is that you can basically in the numerical model, you're able to change the different properties. You can change the height of each of the layers, the permeability of each of the layers, the porosity of each of the layers, but you can also change the PVT. So you can say, I want a different GOR in the different layers, and you can change the initial water saturation per layer. And that's something that we allow for in the numerical model. I think most people maybe are not very aware of this. There's some people that have been using this quite a lot. For example, in the Bakken, specifically for the Three Forks, many people have been using it to use the Three Forks formation as a tracer to try to match water cuts. So they adjust the size of that Three Forks to try to match water cuts because of the initial water saturation of the Three Forks is a little bit different than the Middle Bakken. Okay. And then the next case is the issue that we all are dealing with when we're working with unconventionals. We always want to understand how is our GOR going to change with depletion. And we know that that is going to be very dependent on fluid type and also on the flow regime that we are in. And in Whitson Plus, you have the possibility of doing that in two different ways. You have one of them is in the multi-phase flow and material balance workflow. There you can basically say, okay, this is how my relative ratios of fluids, this is how my OGR and my water gas ratio are going to look like versus pressure. So that is something that you as a user specify. You specify the variation of those properties versus pressure, and with that and the bottom hole pressure forecast that you apply to the well, you're able to generate basically GOR forecast for your well. That is not this is basically not needing any inputs related to relative permeability. So the only thing you have to do is to forecast to provide a forecast of how you think your OGR will change with pressure, which at least for the OGR is something that you can get an idea of from your PVT. And for the water, you also have to do that, and you get the historical data to guide you. With that, then you basically generate a forecast of your OGR profile without having to input any relative permeabilities. If you want to do it with the relative permeabilities, that's something that we always do actually, and that's something that you can do in the numerical model. And there you basically can change the relative permeabilities as you want to basically try to come up with your history match of the gas ratio, and on that when you forecast the well, that those relative permeabilities will be used to also forecast your GOR profile, also the water cut profile actually. Yeah. The number 8 is related to a webinar that we just had from Yelda Barson that discussed the drawdown management or choke management in unconventional wells. And in Whitson Plus, you're actually able to see if this is important for your well. In some cases, you're going to see that your total recovery of oil or your EOR of oil or condensate will be affected by how you draw down your wells. And the way to do that in Whitson Plus is through the numerical model, because there you already have everything baked in. You have the relative permeabilities baked in, you have the PVT that you have input baked in, and you can start to take into account even other things like pressure-dependent permeability, for example. There you just go into the sensitivities feature, and there you define the set of profiles that you would like to do. You see here the cases. You define what's the initial bottom hole pressure, what's the final bottom hole pressure that you want to reach, and what's the time you want to reach that bottom hole pressure. And that basically draws automatically the profile for you, the bottom hole pressure profile for you for the different cases. The difference between the 3 cases here is that I go take a very slow drawdown that takes 1,000 days to reach the minimum bottom hole pressure, moderate one with 500 days, and a very fast drawdown with 100 days. And then in Whitson Plus, you can run those and compare basically the outputs of those, where you get the cumulative oil and cumulative gas for the different scenarios. This will depend on your well, of course. It's not always the same outcome. So I encourage you to try to do this. But basically, in this case, it's just an example that shows that the cumulative oil for the drawdown scenario, where you do a lot of choke management, where you try to keep your bottom hole pressure high and not do a very fast drawdown, you get the highest cumulative oil. Okay. The next thing is related to what we've been talking about also regarding bottom hole pressure calculations. And many of you that have been working with gas lift are familiar with a file that looks like this, or a table that looks like this, where you have a bunch of depths, and with each depth you have a PSO and a PSC. It's pressures that decide when the different valves in your wellbore are open or closed, when the different gas lift valves are open or closed. And we got this request actually very early on from Camino, Wade and the rest of the engineers at Camino. They requested that in general, the software that you use for performing bottom hole pressure calculations, it allows you to input one depth for calculating the bottom hole pressure when you have gas lift. So you have to say, okay, the gas is being injected at this point, when in reality, all you have is a set of depths, and that at a given point in time, different valves will be open depending on the surface pressure. So we implemented that into the software, and you're able to basically, as Graham showed as well, you're able to provide the different depths, the PSO and PSC for each of the valves, and the software will automatically calculate which of the valves are open and will inject through those valves at that given point in time. So you might have today injecting through valve number 3, and tomorrow you might be injecting through valve number 5, and that's all taken care of the software by the software automatically. Okay, and the last case study that I wanted to talk about is the conversion of stock tank rates in the software. So of rates to stock tank, sorry. And that's because many times we have rates that are not measured at stock tank conditions. So we're not measuring the rates for each well, for example, individually, or even for a set of wells, we're not measuring them at sales conditions, at stock tank conditions, which generally would be 1 atmosphere and 60 Fahrenheit. In general, we would measure those at a higher pressure, which is the separator pressure that you'd have in your common tank battery. And when you do that, the rates that you get there basically are not really your final sales rate. And in Whitsun Plus, you can do 2 things with those rates. You can do first, you can go ahead and say, these are my rates, and I want to know that rate when I take it to stock tank, how much does it shrink? And that's important because that shrinkage will allow you to know, that shrinkage factor will allow you to know how much is of that oil is becoming actually sales oil, how much is becoming stock tank oil. And this can be very valuable when you're doing allocation exercises to understand how much, for example, you should be getting from your processing plant. The second thing that you can do is to convert all the rates and the GORs to a common set of separator conditions. That's because maybe at your common tank battery, you've had changes in separator conditions. Many of you, we've seen that suddenly there was a decision made to go from 400 PSI to 150 PSI in the separators. Like, it was just a decision that they had to be made. And then with that change, then you see a jump in your GOR. If you see that jump in your GOR, then suddenly using those GORs for any engineering analysis will not be appropriate, because the fluid that's coming from the reservoir has not changed, not necessarily at least. What really made the GOR change was the change in separator conditions. So in the software, you're also able to correct for those changes in separator conditions, and that's a process that we call common process conversion. And that's key for any type of engineering analysis with data that you have where the GOR is changing because of changing in separator conditions. At least if you don't know if the GOR is changing because of separator conditions, at least if you run this exercise, you'll be able to know if they are changing because of changes in separator conditions or if the change is actually coming from the reservoir. This is something that we see mostly being relevant for people working like in Eagle Ford, linear gas condensates, in Montney, scoop and stack, mostly with linear fluids. Okay, with that, that was my presentation. If there are any questions or comments. I passed the challenge, you see, 10 case studies in 10 minutes.
Well, I need to change the title before distributing. 10 and 15.
15, yeah, you see that.
I
speak as fast as you, Matthias. That's the problem, yeah.
Yeah, that's what I get all the time. I speak too fast. That's my issue. Heard that since I was a kid. So that's great. But no, this is great, Mo. I think a lot of this is kind of a little teaser. We'll of course distribute the slides and whatnot. There's a lot of text on the slides, and some of them are definitely meant for reference. But hopefully that gave you a little bit of an appetite, hopefully, on some of these things that you might want to look more into. I think we'll skip the questions here, Mo, just for this, and jump to the next presentation, which I've kind of gotten a few glimpses of over the last few months, and got the final presentation here the other day, maybe it was yesterday. That's our friends from Crescent Point, so that has done some really impressive RTA work up in the Bakken. So if we can just get, I don't know if you can stop sharing there, Mo, and then we can get Gaurav to unmute and share the screen. There we go. Perfect. So just to introduce the talk a little bit, we've done a lot of work with Crescent Point now, at least for 1.5 years. Gaurav, we started working together, this is like 6 months ago-ish. Feels at least fairly recently. Time just passes very quickly. I've had several sessions. It's been very, very active with providing feedback and using the tool and jumping on calls and whatnot. So that's been great, and I've been truly impressed by a lot of the work that you've been putting together. Not only is it kind of doing a lot of the advanced workflows, but it's also for a lot of wells, which is really cool. So with that, I'll just give the word to you, sir.
Perfect. Thank you, Matthias. Can you, or everybody can see my screen, first of all?
Yeah, perfect.
Perfect. Thank you. So yeah, myself, Gaurav, I'm a senior reservoir engineer with Crescent Point here. And I will just, we are working on Bakken, and we are in the Williston Basin, working towards building some RTA model and using all the available resources through Whitson. A lot of collaboration has been done. So just wanted to showcase whatever is the work and key insights that we have seen based on the rate transient analysis in the Bakken. So here in the agenda, majority of the things when it comes to theory are already covered. So I'll be quickly just skipping through that. What are the things like RTA, metric and fracture gamma, and its impact, modeling water bearing sections, as Mo was mentioning in Bakken, specifically for our three folks. There are multiple layers, and some of the layers constitute to the majority of the water that's coming. So how we, first of all, identify that and how we actually include in the model. Key consideration Bakken, similar things. The workflow that we have been working on, some of the results on the pads. Then the productivity analysis, I think so. Again, Mo mentioned in one of the case studies how we can look into the PNR or RNP plots, try to see how the productivity gets impacted with the way we draw down the wells. So we can take some key inputs and lesson learns from there, try to optimize the drawdowns, and then just to showcase how the RTA predicted EUR goes along with the DCA parameters as well. So yeah, so this is again a similar concept that Matthias mentioned in the beginning. Pretty much it's there are three flow regimes: initial one linear, then transition, and then the boundary dominated. But things doesn't remain so simple. Specifically, when it comes to Bakken, what we have seen is because of some of the presence of natural fractures or whatnot, the flow regimes. There are multiple flow regimes that comes starting from linear to elliptical that can be, and also pseudo radial and pseudo boundary flow, then compound linear, and then the radial or pseudo radial again, and then the final interaction with the next well. But pretty much based on different region or which flow regime you are, we can use different parameters based on RTA to estimate different properties. If we are in initial linear flow, definitely LFP is the parameter we are looking into, which can be linked to the productivity and the other parameters that are very vital for understanding the well and how the completions are being done on that. But once we move towards the end of the flow regime that is pretty much the boundary dominated, we can look into the OIP, which pretty much is the contacted oil in place in the beginning. Again, I think so most of the folks have seen this slide, so consider Whitson. I just trying to just indicate or show you again we start with the PVD and fluid properties post inputting the data. Then now bottom hole pressure calculations. This morning, a lot of conversations were on bottom hole pressure calculations, which is pretty much the backbone data for all the future coming or all the other part of the workflow. So once we are pretty much confident on that, we move into multiphase FMB just to set up a benchmark on the expected OIP. And as Mo was mentioning in the previous slide, again, one of the case studies, you can even go into the forecast if you have the idea about water oil ratio and oil gas oil ratio. So just just a benchmark just for the future. I would say that contacted oil in place and EUR estimates that you'll get. So once you have that, then going to analytical numerical RTA, where starting with the flow regime in the fractional RTA, we try to see where the what are the delta values, and also with the understanding of saturation pressure, we try to see where is the time to end of linear flow. Yeah, again, these are not the correct values because this doesn't include or the multiphase flow behavior or the impact of that. But again, this is just for setting up the benchmark for FCD values, the expected permeability, and the XF. Again, this is just for comparison purpose for the numerical RTA, which will be the next step, where we trying to estimate the LFP. By the way, we try to estimate analytical RTA also for the LFP. And then in numerical RTA, we match the production data, and with a better confidence, we see what is the LFP metrics permeability, XF, and the other parameter. And finally, we go into numerical modeling, where in case we want to include some other water bearing section or some other changes in the property or sensitivity analysis, we try to do that. So pretty much it's the whole workflow. The key considerations that we have back in there, a few expected some of the natural fracture reservoir, again, the extent of which we are still working on it, but we definitely see some of the indications of natural fractures, which creates or comes with some of the complexities in the reservoir. Water bearing section, so below upper three forks, this is expected, and we have seen that in bunch of the wells, we see extra water. And when you include a separate layer of water bearing section, we get better results on history matching and whatnot. So that is also something that was a key insight. Rapidly improving completion parameter and spacing consideration. So we have been improving, optimizing our completion parameters, and thus the wells with the recent or limited well history has one of the best completions, and trying to see how we can compare those with the wells with had a longer history. So that's always a challenge as well. And also wells show longer transient flow regime. This is something that has also come out with the RTA analysis, that it's very easy to sometimes to confuse with the initial linear flow against the compound linear flow. So we need to be very cognizant that we need to see the whole picture before picking the boundary dominated flow. Okay, I'll touch upon quickly upon two topics or that has been part of sensitivity in our RTA models. One of this is the gamma factor. So what we have seen is without sensitivity to pressure, we typically pick a higher LFP, which matches only early data. But it might not match with the GOI, as you can see on the early time data plot. The LFP might be higher, but your OOIPs might not be correct. Similarly, if we try to pick the late time data while matching the late time GOR and trying to pick or estimate the correct OIPs, we might not be picking the right LFP and might be too pessimistic on the LFP parameters. So in order to deal with it, we can include the gamma factor. The most common gamma factor that we have used here is for fractures, of course, for the matrix as well. But in order to guide that, we looked into MPI values or CPG values. In a way, CPG values indirectly can guide you towards what can be this gamma factor, because ultimately gamma factor decides or dictates how much will be the drop in the permeability. So based on the ratio of the MPI, we can indirectly try to relate it with the ratio that we have seen in the permeability numbers. And then based on that, with the changes or estimated averages of our pressures, we can estimate the gamma values. So this has been a part of the study. We have done that for a few of the wells, and also tried to relate it with the lab data on core flooding experiments and try to estimate gamma values. And that has led to a better match in our models. The next thing was I already touched upon then ways the water. So that was also something that we have observed a lot in many of the models. We were able to pick the right LFP. We were able to match cumulative GOR, cumulative oil. But when it comes to water, there was a big gap. So even post changing the relative permeabilities, this gap was not able to fill up because then the other parameters or other history match doesn't go along. So after a lot of permutation and combinations, also without including an extra water layer, we were not able to. But when in the numerical model, we included an extra water layer, we were able to match the water production as well with a good match with the water oil ratio and water cut. So that was also something that was a key insight out of RTA modeling. Now, pretty much we have customized the workflow a little bit based on what we have seen, what we're not. But it's pretty much what I mentioned in the previous slide. So starting with the production data diagnostic analysis, pretty much trying to see how the GOR trend is looking, whether we have the correct bottom hole pressures, how the oil rates and the volume seems to be aligned with that. Then go into decline curve analysis. Decline curve analysis just to set up a benchmark on expected EUR with the understanding of the B values that we have. Once we have that, then looking into flow material balance or IP estimation, and again, a sort of EUR estimate from them. Then analytical RTA, getting estimates of XF, NF, FCD, and other parameters, but also the expected B value from the real-time data. That again feeds back to decline curve analysis, trying to make it fit better with the fractional RTA that we have seen. And then coming back, now some of the parameters that we have seen here works as a benchmark numbers for the numerical RTA, specifically the FCD values. And then based on those, we try to estimate the correct LFP, history match the data, and then move on to numerical modeling for sensitivity and probabilistic analysis. So pretty much based on that, you get a bunch of parameters. These are contacted oil in place, fracture half length, B value, average permeability of SRV, fracture conductivity, production forecast, and EUR. I'll now jump on to some of the results and how we see the results as well. So these are 4 paths. When we started looking into it, they are pretty much 1.5 to maximum close to 2 years of production, but very, very limited production data. So these are the pretty much new completions. Again, they have a bit of a difference in completion, optimizing. So when we look into that, some of the paths seems to be performing really well, but some of them impacted by the depletion, the impact on their productivity, or clearly state that the completion parameters for those pads were not that good. So suppose pad B, if we compare again pad D here, we improve the injection rates, the cluster efficiency of number of cluster per stages, and we saw that even at the early time, the LFPs had a big difference. While for the delta values, you can see that all of them are in transition flow, while a bunch of them are near linear flow. So yeah, as I was mentioning, pad B showed dip in LFP, while some of the half-bounded wells that we have seen shows a better performance, while pad C shows a similar performance as B, except there was one well which is impacted by supercharging. This is also something we have seen, that supercharging effect has been an uplifting factor for some of the wells, where because of the frac or water hammering effect, some of the wells have started improved or showed improved productivity. Also, it seems that the contacted oil in place seems to be about 65 to 75% of the mapped OIP, which was a very motivating factor for us as well. Again, this is just a graphical representation, how we look into those. So pretty much we trying to see how the FMB OIP, again, RTA, numerical RTA OIP seems to be, the LFP derived for different paths, and why we think this is the right understanding where the wells are in terms of their flow regime and also the fracture half length, because it will help us in comparing the completion parameters a little bit. This is a slide I just want to spend a little bit more time on that. This is PNR plots with BHP and GOR. So we are trying to see that are we doing okay with the way we are drawing down our wells, or if we can improve it. So you can see that some of the wells or the pads, the early steep drawdown does impact the late productivity of the well. So you can see that suppose this wallet curve, this is for pad D here. With the drawdown was not that aggressive as compared to maybe the red one, which was pad B. So, but you can see that at a similar time, I think so it was pretty much similar cumulative production as well. The productivity of the wells seems to be better. Of course, there was a bit of a difference in completion parameters, but it seems that even with the closer or similar completion parameters as well, the impact of the initial drawdown or the way you draw down the wells does go along at the later part of the well as well. This might be related to the drop in productivity because of the permeability with pressure, dual phase in near wellbore. If we are looking into, or if there's already a lot of depletion, and if we go the average reservoir pressure goes below the saturation pressure, that can also be there. Near wellbore skin due to sand production. So at the early phase, when we try to we are not able to clean up the wellbore properly, or because of the very heavy drawdown, some of the pore throats of the perforation seems to be plugged, or the wellbore seems to have sort of a sand deposition or the frac sand deposition, and because of that, that thing improves as it goes and the skin develops. So based on all of these and considering the GOR trend that we see, we were able to pick up a sweet spot between the initial IPs that we are getting, or IP 365, and also the drawdown pattern. So that was very insightful and very helpful for us to understand how we should flow back our wells. And this is just a dashboard, how, just a previous workflow, how we go from trying to see the diagnostic plots, the fractional flow, the FMB, numerical RTA, matching of those, and then final numerical modeling and the results based on that. And then again, this is just a comparison of some of the RTA work that we have done and the DCA-based EUR. And also we have been building some of the machine learning models based on the different parameters, and try to see where the three different modeling works give us an idea about EUR. So you can see that because of the limited or initial phase of the well, the productivity seems to be high. So that's why our EUR numbers from RTA are a little bit higher as compared to the DCA parameters. But again, the improvisation will be a continuous process. And similar to that, the machine learning models that are getting improvised are also within the same ballpark. So that gives us the confidence, not only going through a pure physics-based model, but also getting into advanced analytics and also the DCA, trying to see from all three different analysis how our numbers look like. So finally, just a conclusion, results derived from RTA work seems to be converged with the mapped hydrocarbon in place. Fractures and matrices show sensitivity to pressure, so that will be something that will be keep on improving. MPI estimation is done on different timestamps, and we are doing it different paths to get an idea about how the link conductivity of the fractures is changing. And of course, with the better understanding of reservoir characterization based on the history matching, we were able to understand more about the water bearing section, and were able to match the water production in a better way. So this is pretty much the short presentation from my side. If there's any question, yeah, please do let me know.
Very good, sir. Very good. Thank you so much. When I got actually a lot of private notes there that this was a very impressive presentation, and you've done a lot of very good work here. I have a few questions myself, but I see the chat also is getting full here. But I'll start from the top with Rohit's question about if you're able to distinguish between kind of flowback and frac water and the formation water in your model. So basically, or how do you actually do that in practice, I guess?
Yeah, so the thing is, first of all, we have a continuous composition or water analysis that's being done, and based on the difference in the salinity and all, we get to know that how much is the difference in the frac water and the formation water coming along. Also, of course, volumetrics is there. So based on both composition and volumetrics, we are trying to get that. But there's always a case that we are not 100% there. So there's always sort of a fight towards matching the water production sometimes.
Yeah, it is kind of tricky. I was talking to a good friend Ali at Chevron about this yesterday as well. If you have a long period of cleanup with a bunch of water, and you don't put that into the model, it can take a little bit of time before you kind of see clean responses in numerical RTA workflows and whatnot as well. But really good. The second question is when it comes to all your different analyses, you talked about gamma there. Did you use the same gamma value for each analysis, or did you change it for every analysis? And so, maybe you can mention something about the order of magnitude that you were using.
So the thing is, just to be, gamma values are more derived by specific. So let's talk about gamma value from fracture and metrics point of view. For metrics, it's more about the confining pressure and the stress regime that we have. So if the pads are nearby and if we don't see any chances of changing that sort of stress regime or anything like that, we don't change it. When it comes to fracture gamma, pretty much it is defined by the type of proppant that you have pumped, also the understanding that we're getting from MPI. So we try to keep it consistent unless we have a solid evidence that there is a big change in either the completion parameters or the reservoir parameters.
Okay, so just to answer that short, do you keep the gamma parameters the same for all the wells, and then if something
for now,
perfect. And that is also consistent, at least in my understanding, the fact that you had kind of these delta parameters that was now at 0.5 at least initially. So that's also another thing. I see two other questions here with Jorge. Did you have to adjust the in-place volumes to compare EURs from DCA to EURs from your numerical simulation?
Did you have to adjust in-place volume to compare EURs? I would say that when it comes to numerical model, we are still keeping our contacted oil in place as our in-place volumes for the EUR. That's sort of a workflow that we are sticking to rather than expanding it. So we just keep it to the SRV volume that we estimate based on the different analysis, and then try to see where we are on that as compared to DCA. So the answer is not that much, but if it is coming from numerical RTA that much, then we do.
Yeah, sounds perfect. And the last question we'll cover here before we're going to jump on to Leslie's presentation is a question from Whale. What were the range of the variance between the RTA and this multivariate analysis EURs, just percentage-wise ballpark? I think you can.
That's a good question, because ultimately the objective was to shrink down that range. But at this point, after working on 6-7 months on those, we are within the range of 5 to 10% maximum.
Perfect. Thank you so much, sir. Really good presentation again. Excellent stuff. Now we will take a 6-minute break. We'll be back at 10:45 Houston time. Then we'll get Leslie to start with his presentation, and we'll probably go a little bit over. It was actually intended to be a 4-hour session, but we shortened it down a little bit on request. So we'll go a little bit over 11 with the 2 last presentations. So we'll be back in 6 minutes, and we'll start with Leslie's presentation there. And thanks again. Great. So we'll get started with the second last presentation today. It's a presentation I'm really excited about, and it's one of the kind of key, call it consortium deliverables related to doing the multi-phase flow material balance for a wide range of wells. Leslie Thompson, I guess the inventor of this method, this is probably correct, has kind of trying to take this step forward. So with that, Leslie, I'll just give the floor to you. So I think you're muted, Leslie, if you're talking. Just sorry about that. And I actually promised to follow up on a question from Felipe, actually. That was a Felipe, but actually to the last presentation, if you guys have been using the A²K to forecast EURs before having enough data to calculate DCA EURs. So if Gaurav can answer that in the chat, that would be great.
Okay, can you hear me now?
Yeah, sound is great, Leslie. Looking forward to this. Thank you so much.
Okay, thank you. So I am Leslie Thompson, the old guy that stole Graham's here. And today I'm going to bring you up to date on what I've been doing with groups of wells that produce from the same reservoir. So the motivation is pretty obvious. We all see cases where we have wells where we change production in one well and we pick up either more production or more pressure in neighboring wells. So it's obvious we have lots of cases where we have multiple wells all producing from the same volume. And the question is, in those cases, can we group those wells together, treat them as a single entity, and get information about the entire volume drained? And if we can, is there any advantage to doing that over analyzing each well individually? So I'm going to show you a simulated example first to show you how I think about this or how this all works. I'm going to look at one cluster in a 3-well set over half of section. So I have half of a parent, so this is 2,600 feet, half of a section. I have a half of a parent, and then 2 wells in slot 1 and slot 2. I'm looking at 26 feet, so basically one cluster. So my initial run, I'm going to produce the parent only for 2 years. And during that time, the properties of the fracture in slot 1 and slot 2 will be matrix properties. In other words, it's just as if slot 1 and slot 2 don't exist as far as the simulation is concerned. And then after 2 years, I'm going to restart the simulation, but convert the fracture properties in slot 1 and slot 2 from matrix to the actual fracture permeability and porosity. And then I'm going to produce from slot 1 and slot 2 as well. So these are the basic properties that I'm going to be using. The only thing I want you to try and remember for a moment is the initial pressure is 6,500. This is a volatile oil reservoir. And these are the PVT properties straight out of Whitson. Okay, so first the initial run. I'm going to look only at the parent. It produces for the first 730 days, as I said. I've taken the rates and multiplied them by 100 just to make them look more reasonable on these plots. And this is kind of typical of what we'd see in the Permian. So you have some sort of pressure drawdown in the black. And the oil, gas, and water rates are shown on the left-hand side. On the right-hand side, I have a heat map that shows basically where the fluid has come from, or where the mass that you produce, where it can come from. So this is a density distribution at the end of 2 years. And density here is just defined as I show in the bottom. That's the same term that we use in the fluid material balance equation. So I try to line my diagram up with the heat plot. And you can see that most of the mass during the first 2 years, or most of the production is actually coming from the parent, the area occupied by the parent. But there's a significant amount of mass that comes from beyond the parent tips. So way into slot 1, in the slot 1 area. And just to make that more concrete to you, I guess, if you look at pressures, so if you look at just slot 1 and I look at the pressures and saturations along these points that are on the slot 1 fracture, then you can see that the pressure actually changes from one end of the fracture. The end furthest from the parent is at about 6,000 psi, so it's depleted about 500 psi below the initial pressure. And then that drops all the way down to, I don't know, 1,400 psi at the end closest to the parent. Similarly, the saturation of oil and water are definitely not at initial conditions. So slot 1 is not by any means a uniform, it's not starting from a nice uniform condition. It's actually starting from a very strange, very strange initial condition. If you look at the parent only and you just look at this material balance, again, this is straight out of Whitson, you find that its pore volume estimate at the end of the 2 years is about 4265. The actual pore volume is a little north of 13,000. So it's definitely not seeing the whole area, but it's seeing a bit more than the parent SRV. It's seeing about 6% supposedly beyond the tips of the fracture, of the parent fracture. Now, if you restart the model and then you look at all the wells, this shows all the production, and you can see the slot 1, which is this lower solid green line with the solid dots on this plot. The slot 1 production behavior is not that great. I mean, well, compared to slot 2, it's definitely not as good as slot 2, which is kind of what we see anyway in the field. And again, if you look at where the mass came from, you can see again most of it still came from where the parent was, but then the rest of the reservoir is now also significantly depleted at the end of 1,500 days. So we're going to go back again and revisit the FMB plots for all the wells. This is the parent, and initially I had the blue part, so this was the first 2 years. And then after the 2 years, you added this orange data, and I can fit a line to that, and it seems like the pore volume from the parent that the parent thinks it's draining is now actually a little bit bigger than it was before. It went up from 42 to about 44 million barrels. And the percent of the parent SRV increased from 106 to about 111%. Again, the total pore volume is just a little over 13,000 m barrel. Then if I look at the two infill wells, the FMB for the slot 1 is significant. So it's much smaller than even the SRV for slot 1. And FMB for slot 2 is basically close to the SRV for slot 2 well. So all this is pretty straightforward, I hope. And if you add all these things up, then you can see that the total pore volume you get by summing the 3 wells is about 12,000, and it's about 94% or 95% of what's actually there. Okay, so now the question is, can I put all these wells together and analyze them as a single pseudo well? Well, combination of the daily rates is straightforward. You just have to add them up. That's not a big deal. But the question is then, how do you combine the wellbore pressures? And I guess intuitively, I think if you thought about it for 10 minutes, you'd probably think that the way to do that would be probably to weight the bottomhole pressures by the pore volume at any time. I think I can actually show that, but I haven't. In other words, you use the inverse of the FMB at any particular time. So now we're picturing, as the FMB evolves, what you're doing is you're picturing that you're draining pseudo steady state flow from a volume that's increasing with time until it eventually gets to whatever it's going to be at the end. So this will obviously give most weight to the parent well at the beginning, and then at the end, as they all approach their final pore volumes that they produce, then they all be weighted appropriately, I guess. So this is the first thing I thought about, and then I decided that there's no way, this is impractical. There's no way you're going to be able to take slopes of the FMB and try to use that to weight the BHPs. It's just too noisy. And besides, the FMB tends to move back and forth, so getting derivatives is not going to be easy anyway. So I decided to try another approach, which is completely intuition, completely heuristic, and I decided to try to combine the wellbore pressures based on the fraction of the total mass produced by each well at any particular time. I think somewhere in the corners of my mind, I think there's a way to link this approach with the volume approach. But again, I have not made that concrete yet, not even my own mind. So in any case, if I do that, these are the actual wells. These are what they all produce. I showed that before. If I combine the bottom hole pressures, the rates and the bottom hole pressures in the way that I suggested, this is what I get for my pseudo well. And again, you can see that, you know, the pressures at the infill wells are very high at the beginning, but that's pretty much damped out because most of the effect on this in the pseudo well is from the parent well at the beginning. So it's pretty damped when the infill wells come on, and then they eventually go to something that looks, I guess, more or less reasonable. Now, if you do the FMB on this pseudo well, so this is what you get is, and initially for the first 2 years, this is the plot. So this is what we had before. And then when the infill wells come in and you get, you know, all of them combined, you get this new plot down here, which is a much shallower slope, and it hopefully reflects the volume that you're now draining. In this case, I got a pore volume of about 12 million, or 92%, 92.5% of what the actual volume was. So this is just one case I showed. I tried other cases where you don't start the wells, you don't stagger the starting of the wells. You start them all together, for example. I tried different fluids and so forth. So I applied this method to a handful of simulation cases, and it appears to yield a close agreement between individual well analysis, so summing the individual wells and using a pseudo well. Okay, so it looks pretty promising. So again, I have to thank Coursera for letting me look at some of the data, and I looked at a section from a Permian field, and again, this is a volatile oil well, and this is the FMB for the parent, and you can see it's pretty messy. Okay, at the beginning, you got some sort of nice initial slope. And then the well was infilled and bashed. You got something that looks like a much lower slope for a while, but that pretty much goes away with time, and you get this new slope. Then it was worked over. There was a bunch of things going on, and then eventually it came back to more or less the same slope as we had before the workover. So this gives me some number for what the parent well is, and then there are 7 infill wells. And I'm just going to put them up. There's nothing too special about them. And you can add all of them. You can add all of them together. And then you can, again, combine all these wells, all these 8 wells, into one pseudo well. And you can look at that one. And this is what happens. So again, the orange line here is from the parent well by itself. For the first, I guess it's a little over 2 years for this particular well. And then when you combine all of them in a pseudo well, this is what you get. So you get a new deal. And if you compare the results from the sums of the 8 wells and the pseudo well, you can see that they're within a couple of percent, 2 or 3% of each other. So far it looks like the pseudo well method. It gives results that are comparable to analyzing wells individually. Sometimes it's a little bit bigger, sometimes it's a little bit smaller, but it's always within a couple of percent. To me, the nice thing about the pseudo well is that it cancels out variations in individual wells, and it gives a smooth picture for the whole group. I'm going to show you what I mean by that. So clearly, if you look at this well here, this is the parent well, and you were looking at this in real time. I remember looking at this well while I was in Cimarex. There's a lot of angst as you look at this thing develop day by day, and you don't know what the heck it's going to do. So because there's a lot of variation, okay, you start off with a nice smooth curve, then it goes to this crazy thing where it's apparently all the fractures open, it's draining a lot more than it was before, and it starts closing back up again, and you get all sorts of crazy things going on here. But when you add in, so basically the first part is common, this between this and the parent and the pseudo well. But when you add all the effects of all the wells, the infills together, what you get is something much smoother, something much much easier to live with and much easier to I guess, interpret. And so I think that if I were to say what I think is a good advantage of it is that it does this smoothing for you. So you get a picture of the whole group. You get a picture of all this the stuff that's being drained. When I first approached Coursera about looking at some well data for this project to try out some of the methods, they gave me a wine rack configuration, and that wine rack, you had different initial pressures depending on where it was, which that probably is not that difficult to sort of figure out a common pressure to start with. But they all had different fluids as well. And, how the heck do I deal with that? So I decided not to do that one and go to something that was a little bit more simple. This, to me, is a hard problem. I don't think it's straightforward. It might, for sure the guys at Whitson who are experts at PVT will be able to help with that. But so basically, this is where I am now. So I'm going to stop and let you guys tear me apart. Ask whatever questions you want to.
Awesome. Let's say I think another benefit about the pseudo well approach is the fact that a lot of pads in a lot of basins are have all the wells being produced through common tank batteries. So like Bakken is a good example where you have 12 pads all flowing through the this common tank battery. That's the only like direct rate measurement that you're dealing with, and everything else is allocated. And then for most of these wells, at least a lot of them, they also have ESPs, such that you have actually on a single well basis pretty good bottom hole pressures. So in that case, that's another example of when I think the pseudo well approach can be valuable, because then you don't have to kind of break up the wells and whatnot into different subgroups. The other thing I was thinking about on the if you really want to have different PVT and whatnot in all the different wells, then maybe just doing them separately and kind of superposing them would be probably the best thing you could do then. Maybe I'm a little bit unsure. That's just speculation, but no, really good presentation. Just because we're a little bit over time, I have a few questions there, but I'll save those for later, and I'll ask my colleague here, Venkata, that's sitting next to me. So he's going to speak through my mic. So Mo, if you could just let me know if the sound is not coming through clearly enough, just let me know. But I think that should be good. And if you share your screen now, that's just to introduce this chat. That's going to be a little bit of a teaser, what's to come in the software here in the next. Hopefully a few months, I hope. We're getting some very good progress on this work about DFITs. So this is hopefully a presentation for those of you, we kind of including myself, I had literally no exposure to DFIT before, but hopefully after this presentation, at least a little bit of the basics around DFIT, why we need DFITs, and that's, I guess, the goal. Yep. So take it away.
That's the idea. So, hey, good morning, everyone. So, sorry about that. My name is Venkata, but I also go by Teja. As Matthias mentioned, we've been looking into implementing DFIT analysis as a future feature. So I thought I should take the opportunity to share what I learned in a 101 style introduction to diagnostic fracture injection tests. So we keep it simple, look at why, what, and how of DFIT analysis. But happy to field any questions after. So the main outcomes that I look for, or anybody looks for from a DFIT analysis, is minimum principal stress, pore pressure, and permeability. So although these quantities are actually really important through the life cycle of the field development, let me just emphasize some of the reasons why we need these quantities. So the minimum principal stress could be used for fault seal analysis, could be used to avoid lost circulation or maintaining wellbore stability while drilling. It can also be used during completion and production for estimating the net pressure, modeling hydraulic fractures, and their geometry. predicting long-term sand production and subsidence, etc. So now I'll talk about a little bit about the pore pressure, but we all know that it's important to know the pore pressure at different areas in the field. It characterizes the depletion across the field and vertically in layers as well. It determines the extent of drainage from a well, so we can optimize the well spacing. And the last one, permeability, is actually a really important outcome of the DFIT analysis. And if we're lucky enough to find a good estimate of minimum principal stress and pore pressure, we can actually go ahead and estimate permeability from a DFIT analysis. And why that's important is because DFIT analysis uniquely derives an in situ estimate of permeability. So we can use that to actually overcome the non-uniqueness and assumptions that we have when we're doing permeability analysis from cores or RTA. So, and in other news, the permeability actually matters a lot in terms of deciding the optimal well spacing, and different permeabilities will lead to different net present values in combination with spacing. Apart from these three main objectives, we also do intermediarily calculate like the effective shut-in pressure, formation leak-off coefficient, and net pressure and average aperture of the fracture, etc. But if you have to remember three things from this presentation about DFITs, you get these three outcomes. So let's get into the what is DFIT exactly. So the DFITs are actually low volume, pure water injection tests. They can be done in low permeability or high permeability wells, but there's differences there. And at sufficient rates and pressures to create a dominant hydraulic fracture. So we inject at sufficient rates and pressures, we create a dominant fracture, and then we shut in the well. Once we shut in the well, the shut-in could last days, weeks, or sometimes months, depending on the well. But we monitor the pressure fall-off during shut-in to interpret the data for reservoir characteristics. So the plot on the left shows the typical test sequence in DFITs, and we see a plot of pressure versus time. The rates are not displayed here, but essentially I want to just highlight the major components of the test sequence. So the part one is the wellbore storage, where we're ramping up in pressure and rates until the leak-off point or the formation breakdown point. From the formation breakdown point at 2, this peak over here, we actually, let me get the laser, yeah. So we actually go into phase 3, where we actually continue the pumping schedule, and that leads to fracture propagation. And once the fracture propagates, the number 4 indicates the time when we shut in the well. And essentially, we see, signatures in the shut-in transient for fracture closure, and then part that's not shown in this plot is like after closure transients. So with that typical test sequence in mind, let me just introduce to you the main plots that are involved in the interpretation of a typical DFIT. So the first plot I'd like to introduce is just like the previous slide, is the bottom hole pressure versus time and rate versus time. Plotting this actually gives me a good idea of when the well was shut in, how much rate was used, and what was the ramp up cycle or things like that. And essentially, what I do is I look at the shut-in time and plot the shut-in pressures in the next plot. So in this plot, what I have is just the pressures from the shut-in, from the beginning of the shut-in, and I've plotted those against G time. I'll introduce G time later, but essentially it's a key plot in DFIT analysis where we could either work with the derivative as dP over dG or G times dP dG, which may have been typically used. So the points in orange are the dP/dG, and the points in blue are the G/dP/dG. The blue points were traditionally or typically used, but we'll be using the dP/dG and the SP 2019 123 workflow for all estimations. So the third plot that's also important is the difference in pressure and its well test derivative. This is a typical well test derivative that we calculate in well testing as well. What I'm plotting here is the difference in my effective shut-in pressure and the bottom hole pressure. And I see that since there is leak off, the bottom hole pressure reduces, so the delta P goes up, and we can then look at the derivative to analyze these transients. So in this derivative, we can see that the peak at dP/dt is when the fractures have closed, and beyond that, we have the post-closure transients or after closure transients. So in this part of the data, I want to identify the same flow regimes like in well testing, like linear flow or radial flow. And given that I can find something like something like a linear flow regime, I can then plot the last plot, which is the pressure versus the inverse square root of time. So I'll take the part of the data that's in linear flow and I'll plot it against the inverse of square root time. So I get something like this. And when I take this plot and extend it to get the y-intercept, that y-intercept is my pore pressures. But we'll go into that in more detail in the upcoming slides. But essentially, these are the 4 plots that I'll be using. So let's get into the how, where I'll be discussing a little bit of theoretical background, but mostly just giving you a walkthrough of how to interpret like a DFIT analysis. So the main theoretical background that I wanted to introduce here is Carter-Leakoff. The Carter-Leakoff provides the fundamental physics that governs the fluid leak-off rate from a high pressure source. And it is derived from 1D solution to fluid flow in a porous medium. And it essentially represents the cumulative fluid leak-off, which is proportional to the square root of time from the beginning of leak-off. Now I said time, but what does that mean? Because different locations in the fracture have actually started leaking off at a different time. So essentially, that's what brings me to the next concept, which is the G function and the H function. So think of these as superposition time functions used for analyzing shut-in DFIT pressures. They're used to estimate the minimum principal stress given by SH-min. And I'll go over that in more detail in the next slide. But essentially, once we do that, we can also look into late time impulse flow solutions. So this is the part of the data that is after the fractures have closed. But because we can also use this part to estimate pore pressure, you can also use this part to estimate permeability and indicates that late time data. So now this slide may look busy, but let me walk you through it. So on the left, I have the details about the G function, and on the right, I have the details about the H function. On top, the equations are actually Carter-Leakoff equations written in terms of G time over here and H time over here. And what you can see is that the G time is actually controlled by Carter-Leakoff and assumes constant fracture pressure. This may or may not be true, but this is kind of obvious when you look at how the G function is constructed. The shut-in time is actually, time since shut-in is actually given by delta T, and the injection time is given by TE. And you can see that pressure does not come into the picture at all. And hence, we have these assumptions where we assume constant fracture pressure. On the other hand, the H function accounts for deviation from Carter-Leakoff and declining fracture pressure. So that's why you see this one-dimensional time convolution integral, where the H function can be given as a time convolution along the pressures. And so that's why we can account for declining fracture pressure. So the main reason why we do the dp/dg plot is because this derivative is interpreted for wellbore tortuosity, effects of closure, and leak-off. So if you look at the form of the derivative, dp over dg, then it is actually the leak-off rate with respect, the derivative of the leak-off rate with respect to g time divided by the system storage coefficient. So I'll explain that a little bit later, but these are the two main components that go into it. And the minimum dp/dg may be still elevated due to near wellbore tortuosity, but I'll show you that in the next slide. The other thing I wanted to mention was that the H function, being independent of the declining fracture pressures, is also used for the construction of relative stiffness plots, which are important when you cannot use a G function to estimate the minimum principal stress. So with that, let me just show you a typical interpretation of a G function plot. So given a G function plot, this is my plot with the bottomhole pressures on the left y-axis. I've plotted the derivative in red on the right y-axis, and I have G time on the x-axis. So the first thing you see is that there's a precipitous pressure drop at very early time, and that's an indication of severe near wellbore tortuosity. This may not be the case for vertical wells, but for horizontal wells, this may be quite substantial. The next thing I notice is this point here, which is the minimum dp/dg. So this point here represents the part of the data that is least affected by what's on the left and what's on the right. So what's on the left is severe near wellbore tortuosity. What's on the right is actually fracture closure. So as this derivative drops, reaches the minimum dp/dg, it starts picking up again when the fractures begin to close. So because this is a DFIT analysis, and the way this is different from conventional well testing analysis is because we assume the fractures are dynamic, and that's what we see here. We see that once the fractures begin to close, the system storage coefficient reduces, and essentially it creates a peak in the DPDG like this. So once I have the minimum DPDG, I also know that this section here, which is a roughly constant pressure inside the fracture, can be used for estimating the effective shut-in pressure. So the literal shut-in pressure would be somewhere high up over here, 11,000, but the effective would be calculated from this pre-closure transient or the ideal nullity period where the fracture pressure may be assumed to be roughly constant. And then what I can do is take the minimum DPDG, add about 10%, which is essentially the part where we get the contact pressure. So once we add 10%, and that essentially means the point where the fractures have begun coming into contact, and we get the contact pressure. And heuristically, the minimum principal stress is found by subtracting about 75 psi from the contact pressure. So the reason for that is because there are some assumptions that go into it, like the Young's modulus or the width of a fracture, and might be iterative, but the uncertainty there is around 100 psi. This gives you the minimum principal stress. The next thing I wanted to show you is how the increase in the derivative causes fracture closure. And once the fractures cannot close anymore with a residual aperture, there is afterflow. And this part of the data is actually this peak over here that is important, because if I'm using the H function to calculate my permeability, then I use 2 points. If I'm using the G function, I use 1 point. That's why H function is supposed to be better. But let me talk about what happens after this peak. What happens after this peak is a post-closure transient. It may show impulse flow signatures or problems sometimes. So what I would do is take this after closure transient and plot it up to get my impulse flow signature slopes and calculate pore pressure. So that's what my next slide is about. So in this step, we found the minimum principal stress from my previous slide. In this step, we take that late time impulse flow and plot it up against dp and a derivative of dp with respect to natural log of t on a log-log plot. This looks like a typical well testing plot, but the key here is to identify these flow regimes in the after closure section. So that would be after this t dpdt peak. And so these are two examples where after the peak, I see a half slope in dpdt. So I can get the pore pressure by plotting the bottom hole pressure and the square root of inverse of square root time. I'm sorry about that. So inverse of square root time. And for impulse radial flow, if I see a unit slope over here, which is kind of rare, I then plot the bottom hole pressure of that section with the inverse of time. So once I do that, if I extend that to get the y-intercept, that gives me my pore pressure. But I'd like to remind you that these post-closure transients can also be used to estimate the permeability. So with that, let me just give you a theoretical introduction about how permeability is calculated. So first, we pick the data and equations to work with. There are 4 methods. You can either use pre-closure methods or post-closure methods. And within pre-closure, like I mentioned earlier, you can use either the G function or the H function. In the post-closure methods, you can use either the impulse radial, which I showed you with a negative unit slope, or the impulse linear flow, which is the negative half slope. Each method has its own set of equations. Next, we have to assume a fracture geometry because, like I said, we consider the fact that fractures are dynamic in DFITs. So it's common to assume like radial fractures, but for PKN fractures, it needs an assumption of the equations for stiffness change depend on the assumed geometry. And that's important because the last step is to write mass balance for boundary conditions. So this is essentially, we have an injected volume, we have pressures, we can actually write the mass balance with boundary conditions at the end of injection, at minimum DPDG, or at peak DPDG. And the total volume injected is known or measured in the DFIT test. And we consider wellbore storage and leak off, and that gives us these 2 parameters, the radius or the fracture dimension and the leak off coefficient, which are then used to calculate the effective permeability of fluid flow. So the key here is that we have to find the combination of fracture extent and leak off rate that satisfy the equations for the same injected volume as measured in the DFIT test. So that forms a pretty good boundary condition for us. And with that, I'd like to just summarize with key takeaways. So DFITs are used to provide an estimate of minimum principal stress using the new compliance method. So what we just discussed in this presentation was a new compliance method, and that's different from the tradition typically done from how it was typically done in the past. We used a dPdG instead of G times dPdG. And I'd like to draw your attention to the third point here, which is essentially if we use the tangent method, which was typically used since 2009, it has shown that it overestimates the resolved quantities by up to 100 times. So the result is that we get into suboptimal well spacing and our NPV is largely reduced. So with that, I'll also point out that DFITs provide that independent permeability estimate that you're looking for to resolve effective fracture area RTA at A√K. And the other thing I'd like to mention is that only good or adequate indication of compliance responses can be used for K estimation. I can discuss this further, but essentially what I'm trying to say is that if I don't have a good confidence in my pore pressure or my minimum principal stress, I cannot go ahead to estimate permeability with this test. So some of the reasons that could cause a bad indication of compliance response or high uncertainty in my first two resolved quantities is instant closure, severe wellbore tortuosity, natural fractures, operational issues. And so in that cases, I won't estimate permeability. The last thing that I want to mention is that it still comes with some pitfalls. For example, pre-closure permeability estimate may be about 2 to 3 times higher, and post-closure estimate is usually lesser and more reliable. And that's what is used in most engineering calculations. But however, we may not have that post-closure K estimate because it needs a longer shut-in. And the pre-closure, so usually what people do is use the pre-closure estimate with a safety factor of like 2 to 3x for using in reservoir engineering calculations. And then we've also seen some reports of like false radial flow regimes, typically seen in gas shales. And using that for like a post-closure permeability estimate also leads to a 10 to 100x overestimate. So just some things we need to be careful about. But that's pretty much what I had for y'all. Happy to take any questions. Thank you.
Awesome. The question we got very early on was, are we going to have the DFIT module in Wits and Plus? And the question or the answer to that is yes. So for those that are in the well test domain, we'd like to see more stuff there. DFIT just had the shot pressure group in there, getting in the DQI thing as well. Tejas is spearheading a lot of that activity. So our goal is to have at least a DFIT up sometime this summer, and at least the release we have then. So we'll see and keep you guys posted on that. We're a little bit over time here. We're 20 minutes past the time, so I'll end the call there and thank all of you for attending. We're looking forward to seeing you all in the next knowledge sharing session in June, and also there are courses coming up here as the year continues to progress. So appreciate it, and you have a good rest of the day. Cheers.